settle in for a moment. Wherever you are right now, just allow the space around you to hold you. Notice the quality of the air in the room, the way it feels on your skin. Is it cool from a window left open, or warm from the hum of a nearby machine? Feel the weight of your own body, the gentle, persistent pull of gravity that is, in its own quiet way, the planet's oldest conversation with us. Perhaps you can hear the faint, ambient sounds of your home or the world outside, the soft rush of a distant car, the creak of floorboards settling, the almost imperceptible buzz of electricity in the walls. These are the sounds of your world, here, now. Tonight, we aren't going to rush. There are no deadlines here, no arguments to win. Curiosity, real curiosity, can take its time. It doesn't need to shout. It can afford to be patient, to turn things over slowly, to look at them from different angles without needing an immediate answer. And so, in this quiet moment, let's just hold a single question. Let's not try to solve it right away, but simply let it rest in the mind, like a smooth, heavy stone in the palm of your hand. It's a question about a world that is impossibly distant, a world so alien it might as well be another planet entirely. Yet, it was this planet. It was this very same sphere of rock and water and air, turning through the same silent space. The question is this: what was it like to stand on the Earth to breathe its air in the last moments of the Permian world? What did it feel like as the single greatest catastrophe in the history of complex life began to unfold? This isn't a question about blame or about a single cinematic cause. It's not about finding a villain, be it an asteroid or a volcano. It's a sensory question. It's a question about the quality of the light filtering through the leaves of plants that no longer exist. It's about the temperature of the water in an ocean that had a different shape, a different chemistry, a different breath. It's about the feeling in the air just before the storm, a storm that would last for tens of thousands of years and nearly erase the book of life entirely. To even begin to approach such a question requires us to slow down, to set aside our human-scaled sense of time, where a century feels like an eternity. We need to learn to think in layers of rock, in the subtle chemical whispers left behind in ancient mud. We are looking for a ghost, a phantom world, and the only clues we have are written in a language of stone and isotopes. The evidence is fragmented, buried under 252 million years of planetary history. It's an investigation conducted at a distance that is almost impossible to comprehend. And yet, the desire to know, to reconstruct that lost world, is a deeply human one. It comes from the same place that makes us look up at the stars and wonder what's out there. It's a way of asking a much larger question about our own place in this long, strange story. What does it mean to live on a planet that can change so profoundly? So tonight, let's just begin. Let's start the journey back, not as conquerors of knowledge, but as quiet observers. We will travel to a time when the continents were merged into one vast, unfamiliar landmass, a world of giant amphibians, strange mammal-like reptiles, and sprawling arid deserts. We will try to piece together, from the faintest of clues, what it felt like to be alive then. We will listen for the echoes of a world on the brink, a world that was, in its own way, as beautiful and complex and complete as our own. And as we do, we may find that this ancient, long-dead world has something to say about the fragility and the resilience of the world we are breathing in right now, in this very room. The journey is the purpose. The exploration is the answer. Let's simply begin by asking what it was like. Our exploration tonight is guided by a particular spirit of inquiry. We are not here to arrive at a final, unshakable verdict. The story of the deep past is not a courtroom drama where we can cross-examine witnesses and declare a definitive truth. Instead, it's more like assembling a mosaic from fragments found scattered across a vast and weathered landscape. Many of the pieces are missing. Some are faded, some might not even belong to the picture we're trying to make. Our task, then, is one of careful and provisional reconstruction. We are building a model, a working hypothesis of what this world was like. And it's important to hold that word, model, in our minds. A model is not the thing itself. It is a simplified representation that helps us think about a complex system. A weather forecast is a model. An economic projection is a model. Our understanding of the distant past is also a model, constantly being updated as new fragments of evidence come to light. This means we must be comfortable with uncertainty. We must be willing to say it seems likely or the evidence suggests, rather than this is what happened. This isn't a weakness in our understanding. It's an honest reflection of the nature of the evidence. When we talk about events that occurred 250 million years ago, certainty is not a luxury we can afford. In fact, a deep skepticism of absolute claims is one of the most powerful tools we have. It keeps our minds open. It forces us to continually test our own assumptions and to look for evidence that might contradict our favourite theories. So, as we proceed, we will be operating with a few clear guardrails. First, we will always try to distinguish between the evidence itself, the chemical signature in a rock, the pattern of fossils in a geological layer, and the interpretations of that evidence. The rock is the fact. The story we tell about the rock is the inference. Both are crucial, but they are not the same thing. Second, we will favour mechanisms over simple causes. The question is not just what happened, but how it happened. We're interested in the cascade of events, the feedback loops, the way that one change in the planetary system could trigger another, and then another in a chain reaction. We are looking for the processes that drove the world from a state of relative stability into a state of catastrophic collapse. This systems thinking approach helps us move beyond a simple whodunit narrative and into a more nuanced understanding of planetary behaviour. Third, we will hold multiple hypotheses in our hands at the same time. While one explanation might seem more compelling or have more evidence supporting it, we won't discard other possibilities out of hand. Science progresses by comparing competing explanations. By laying them out side by side, we can see where they overlap, where they differ, and what kind of evidence might help us distinguish between them. This is not about creating a false sense of equivalence. Some theories are indeed much stronger than others, but it is about acknowledging that our knowledge is incomplete and that new discoveries could change the entire picture. Finally, our method will be one of slowness and patience. We will build our understanding layer by layer, starting with the most concrete pieces of evidence and gradually moving toward the more abstract and complex interactions. We will take detours to define our terms, to examine our tools, and to question the limitations of what we can know. This is not the fastest way to get to an answer, but it is the surest way to build an understanding that is both robust and flexible, one that can accommodate new information without shattering. Our goal is not to leave you with a neat, tidy story that answers every question. It is to leave you with a richer, more textured sense of the questions themselves. It is to equip you with the framework to think about this ancient world, to appreciate the ingenuity of the science that allows us to glimpse it, and to sit with the profound mystery that still remains. This is an exercise in thinking like a deep-time detective, where the crime scene is the entire planet and the witnesses have been silent for 252 million years. Let's proceed with the humility and the curiosity that such a task requires. So, let's begin right where you are, in this room. Just for a moment, let your awareness expand to the physical space you occupy. Feel the texture of the surface beneath you, the fabric of a chair, the weave of a carpet, the coolness of a wooden floor. These are materials. They have a history. The wood came from a tree that drew carbon from the air. The fibres in the carpet may have come from petroleum, which is itself the remnant of ancient life, buried and transformed over immense spans of time. The very atoms that make up the walls around you were forged in the hearts of long-dead stars. You are sitting inside a nested story of time right now. Notice your breath, the gentle, rhythmic in and out. With each inhale, you are drawing in a mixture of gases, mostly nitrogen, about 21% oxygen, a tiny fraction of carbon dioxide. This specific atmospheric blend is not an accident. It is the product of billions of years of geological and biological activity. The oxygen you are breathing at this very second was likely produced by phytoplankton, in the ocean, or trees on land, perhaps thousands of miles away. You are participating in a planetary-scale respiratory system, a conversation between life and atmosphere that has been going on for eons. The air in your lungs is a physical link to the entire biosphere. Now, consider the water that is in your body, making up more than half your weight. That water has been on an incredible journey. It may have been locked in a glacier, deep in the ocean, or part of a cloud that crossed a continent. It is part of a cycle, the great hydrologic engine that moves water from sea to sky to land and back again. The water in your cells is the same water, chemically speaking, that filled the rivers and oceans of the Permian world. It is an ancient and constant traveller. We ground ourselves in these concrete sensory realities, the chair, the air, the water, because it's easy to get lost in the abstractions of deep time. A number like 252 million years is so large that the human mind can't truly grasp it. It becomes a kind of meaningless placeholder. But the physical processes, the fundamental laws of chemistry and physics, are the constants that connect our world to that one. Gravity worked the same way. Water still boiled at a certain temperature, given a certain pressure. Carbon atoms still formed the backbone of life. By starting with the tangible, present tense experience of being in a body, on a planet, we build a bridge. We can take the familiar physics of our world and use them to explore the unfamiliar biology and geology of another. Imagine for a moment that we could transplant this room just as it is back to the late Permian. What would be the first things you'd notice? The air, for one. The oxygen level was likely lower than today, perhaps around 16% instead of our familiar 21%. Your breathing might feel laboured, like being at high altitude. The carbon dioxide level, however, was much, much higher. Not just a little higher, but perhaps 5 to 10 times higher than it is today. This wouldn't be something you could directly smell or taste, but it would have profound effects on the planet's climate and the chemistry of its oceans. The ground beneath you would be part of the supercontinent Pangea. Depending on where you were, the nearest ocean could be thousands of kilometers away, across a vast, arid interior. The very concept of continents as we know them would be gone, replaced by this single immense landmass stretching from pole to pole. The light coming through your window would be filtered through a different sky, and it would illuminate a landscape of bizarre plants, towering glossopterid trees, relatives of modern ferns and cycads, but no flowers. Flowers had not yet evolved. The sounds you would hear would be utterly alien. No birdsong, no buzzing insects in the way we know them. Instead, you might hear the heavy tread of giant tusked herbivores called dicynodonts, or the guttural calls of strange saber-toothed predators that were more closely related to us to mammals than to any modern reptile. By placing our familiar sensory world into that ancient context, the Permian stops being a distant abstraction and starts to become a place. A strange place, a dangerous place, but a real place nonetheless. This is the imaginative work we must do. We must use the knowns of our own experience to build a scaffold from which we can reach into the deep unknown. The feeling of air in your lungs, the pull of gravity, the warmth of sunlight, these are our anchors, and from this grounded place we can begin to follow the clues back, through the layers of stone and time, to understand what happened when this entire sensory world was dismantled. Why does this question matter? Why spend our time and energy trying to reconstruct a world that vanished 250 million years ago? It can seem like an act of pure, esoteric curiosity, a puzzle for paleontologists and geochemists with little relevance to our lives today. But the Permian extinction, often called the Great Dying, holds a mirror up to our own world, albeit a distorted and ancient one. Its importance lies not in finding simple one-to-one analogies, but in what it reveals about the fundamental rules of how a living planet operates, how it maintains stability, and how, under certain pressures, it can catastrophically fail. First, studying this event gives us a vital sense of perspective. The story of our planet is vastly longer and more dramatic than the story of our own species. We have existed for a mere sliver of geologic time, a fleeting moment atop a deep, deep history. For most of Earth's past, the world was unrecognizably different. Understanding the sheer scale of this history and the magnitude of the changes the planet has undergone is a profound exercise in humility. It reminds us that the conditions we take for granted, The composition of the atmosphere, the stability of the climate, the configuration of the continents are not permanent. They are temporary states in a long and ongoing planetary evolution. The Permian extinction shows us the Earth system pushed to its absolute limit. It wasn't just one thing that went wrong, it was everything, all at once. The event serves as a planetary-scale stress test. By studying how the systems failed, how the carbon cycle spun out of control, how the oceans lost their oxygen, how the web of life collapsed, we learn about the thresholds and tipping points that are inherent to the Earth system itself. It's like studying a bridge collapse to understand the principles of engineering. You learn the most about a system's resilience by examining its moments of failure. This ancient catastrophe reveals the hidden wiring of the planet, the interconnectedness of the atmosphere, the oceans, the land, and life itself. We see how a massive geological event in one location, like the volcanic eruptions in Siberia, could trigger a global domino effect that rippled through every ecosystem on Earth. It teaches us that you cannot fundamentally alter one major component of the Earth system, like the carbon cycle, without expecting profound and often unpredictable consequences in all the others. The story of the Great Dying is also a story of survival and recovery. Life was nearly extinguished, with estimates suggesting that up to 96% of marine species and 70% of terrestrial vertebrate species went extinct. Yet, life did endure. The survivors, those few species that made it through the crucible, became the ancestors of the world that followed. The extinction cleared the slate, creating ecological opportunities that eventually allowed for the rise of the dinosaurs in the subsequent Triassic period, and much, much later, after another extinction, the rise of mammals, and eventually ourselves. Our own evolutionary story is therefore deeply entangled with this ancient collapse. We are here in part because of the vacancies it created. The recovery process itself is also deeply instructive. How does a biosphere rebuild itself from scratch? It took millions of years for ecosystems to regain a semblance of their former complexity. This tells us that planetary-scale damage has a planetary-scale recovery time. The timescale of destruction can be terrifyingly fast, while the timescale of healing is punishingly slow. This asymmetry is perhaps one of the most sobering lessons from the Permian. It underscores the preciousness of the complex, mature biosphere we have inherited. Building it took eons, dismantling it can happen in a geological blink of an eye. And so, while we must be incredibly careful not to draw simplistic, alarmist parallels, the Permian extinction serves as a crucial case study. It is the most extreme example in the geological record of what happens when a massive injection of greenhouse gases pushes a planet's climate system into a new, hostile state. It allows us to test our climate models, our understanding of ocean chemistry, and our theories about ecosystem resilience against a real-world event of terrifying magnitude. The question of what Earth was like during the Permian extinction is not just about the past. It's about understanding the very character of the planet we live on. It is a story about thresholds, feedbacks, and the intricate dance between geology and biology that makes our world habitable. It is a story that, once understood, changes the way you see the sky, the ocean, and the ground beneath your feet. As we begin to assemble the pieces of this ancient puzzle, we can see several key threads of inquiry emerging. These are the lines of evidence we will need to follow, the mysteries we will need to explore, and they will form the backbone of our investigation. We will introduce them here briefly, as signposts for the journey ahead, and we will return to each one in greater detail later on. Think of these as open loops, questions left hanging in the air that we promise to revisit. The first thread leads us to a specific place on the globe, modern-day Siberia. Buried beneath the forests and tundra of this vast region lies a geological feature known as the Siberian Traps. This is not a series of individual volcanoes, but a massive volcanic province, one of the largest known in Earth's history. Over a period of perhaps 1 million years, but with pulses of intense activity, an immense volume of lava erupted and poured across the land. But it wasn't just the lava that mattered. These eruptions also released staggering quantities of gases into the atmosphere: carbon dioxide, methane, sulfur dioxide. We will need to ask, how could a geological event in one part of the world trigger a global collapse? What was the mechanism that translated localized volcanism into a worldwide extinction? This thread is about the trigger, the initial shock to the system. The second thread takes us from the land to the sea. The fossil record shows that the extinction was even more devastating in the oceans than it was on land. Entire marine ecosystems, like the vibrant reef systems of the Permian, vanished completely. The clues here are not just in the fossils, but in the chemistry of the sedimentary rocks that formed on the ocean floor. These rocks tell a story of oceans that were becoming increasingly acidic, and perhaps more terrifyingly, losing their oxygen. We will have to investigate the concept of ocean anoxia and euxenia, a state where the water is not only devoid of oxygen, but also poisoned with hydrogen sulfide. What would it be like to stand on a shore overlooking a toxic, purple-hued ocean? This thread is about the propagation of the crisis, how the initial shock was amplified by the planet's oceans. The third thread concerns the very shape of the world itself. During the late Permian, nearly all of the Earth's landmass was fused into the supercontinent of Pangea. This geographic arrangement had profound consequences for global climate patterns and the distribution of life. A single, giant continent creates vast interior regions that are incredibly dry and subject to extreme temperature swings. It also affects how ocean currents circulate heat around the globe. We must ask, did the unique geography of Pangea make the world inherently more vulnerable? Did this continental arrangement create a planetary system that was somehow brittle, predisposing it to collapse when the shock from the Siberian traps arrived? This thread is about the context, the pre-existing conditions that set the stage for the catastrophe. These three threads, the volcanic trigger, the oceanic response, and the continental context, are not separate stories. They are deeply intertwined. We will need to see how they connect, how they fed back on each other, to create a perfect storm of environmental collapse. We will pick up each of these threads in turn, examining the evidence behind them and exploring their implications. For now, just hold them in mind as the core pillars of the mystery we are about to unravel. Before we dive deeper into the evidence, it's essential to establish a few working definitions. The language used to describe deep time and mass extinctions can be precise, but it can also be laden with assumptions. By clarifying our terms now, we can build our understanding on a more solid foundation. Let's start with the word extinction itself. In its simplest form, extinction means the termination of a species. When the last individual of a species dies, that species is extinct. It's gone forever. This is a natural part of the evolutionary process. Scientists refer to the normal, ongoing rate of extinction as the background extinction rate. Species are always going extinct, just as new species are always evolving. It's a constant churn. A mass extinction, however, is something different altogether. It is a statistically significant increase in the extinction rate in a geologically short period of time, affecting a broad range of different ecosystems and groups of organisms across the entire globe. It's not just a few species winking out, it's a wholesale collapse of the biosphere. There have been 5 of these major events in the history of complex life, colloquially known as the Big Five. The Permian Triassic extinction was the most severe of them all, which is why it earned the nickname the Great Dying. Next, let's place ourselves in time. The term Permian refers to a geologic period. Geologists have carved up Earth's 4.5 billion year history into a hierarchy of time units: eons, eras, periods, and epochs. This geologic timescale is based on the layers of rock or strata and the fossils found within them. The Permian period is the final period of the Paleozoic era. It began around 299 million years ago and ended with the mass extinction event around 252 million years ago. So when we say we are exploring the end Permian world, we are talking about a specific slice of time, 250 million years in the past. The event itself, the extinction, marks the boundary between the Permian period and the next period, the Triassic. This is known as the Permian Triassic boundary, or PT boundary. When you see a geologist pointing at a specific line in a rock outcrop, they are often pointing to one of these boundaries, a physical manifestation of a profound change in the state of the planet, preserved in stone. Another key concept is the idea of proxies. Since we cannot go back in time with thermometers and air sampling kits, scientists rely on indirect evidence, or proxies, to reconstruct past environments. For example, the ratio of different isotopes of oxygen in the shells of ancient marine organisms can tell us about the temperature of the water they lived in. Similarly, the ratio of carbon isotopes in sedimentary rocks can give us clues about the state of the global carbon cycle. These are chemical fossils. We are not measuring the temperature or the atmosphere of the Permian directly. We are measuring a chemical echo it left behind in the rock record. Understanding this is crucial. It means our knowledge is always mediated through these proxies, and the interpretation of these proxies is a complex science in itself. Finally, let's talk about our assumptions. We are assuming that the fundamental laws of physics and chemistry have remained constant throughout Earth's history. This is a foundational principle of geology called uniformitarianism, often summarized as the present is the key to the past. It doesn't mean that the Earth always looked the way it does now, or that the same processes were always active. The Permian world was clearly very different. But it does mean that we can use our understanding of, say, how carbon dioxide traps heat today to understand its effect on the climate 252 million years ago. We assume that gravity, thermodynamics, and atomic behavior have not changed. Without this baseline assumption, we would have no way to interpret the clues left in the rocks. So, to recap, we are investigating a mass extinction, a rapid and global collapse of biodiversity that occurred at the Permian-Triassic boundary about 252 million years ago. Our evidence will come from the rock record, and we will use chemical proxies to interpret the environmental conditions of that time, all based on the assumption that the fundamental laws of nature are constant. With these definitions and guardrails in place, we can now begin to paint a picture of the world as it was, just before the fall. To understand the scale of the collapse, we first need to appreciate what was lost. The world of the late Permian was not a primitive or simple place. It was a mature biosphere, the result of hundreds of millions of years of evolution. It was teeming with life that was complex, diverse, and in many ways utterly bizarre from our modern perspective. Let's start on land. The dominant terrestrial ecosystems were not ruled by dinosaurs. Their time had not yet come. Instead, the large land animals were dominated by a group called the synapsids. The synapsids are sometimes misleadingly called mammal-like reptiles, but they are actually on the evolutionary line that leads directly to mammals. In fact, we are synapsids. The Permian was their golden age. Among the most common herbivores were the dicynodonts. Imagine creatures that looked something like a cross between a pig and a turtle, ranging from the size of a rat to the size of an ox. They had stout, barrel-chested bodies, beaked faces, and often a pair of prominent tusks. They were incredibly successful, found all over the supercontinent of Pangea, and they were the dominant plant-eaters of their time. They browsed on the tough vegetation of the Permian forests and plains. Hunting these herbivores were formidable predators, most famously the Gorgonopsians. These were the apex predators of the late Permian. Picture a creature the size of a large bear with a powerful muscular build and most strikingly a pair of long, saber-like canine teeth. They were fast, powerful killers, the wolves and lions of their age. The Gorgonopsians and dicynodonts were part of a complex food web that also included many other smaller synapsids, large amphibians that resembled crocodiles, and early reptile groups. It was a world of tusks and sails and strange postures, a dynamic and flourishing terrestrial ecosystem. The plant life was equally alien. There were no grasses, no flowers, no fruit-bearing trees. The great forests of the southern parts of Pangea were dominated by glossopterids, a type of seed fern with large tongue-shaped leaves. In the north, conifers, similar in some ways to modern pines and firs, were more common. The understory was a mix of ferns, horsetails, and cycads. It would have been a world of greens and browns, without the vibrant colours of flowering plants that we are so accustomed to. Now let's turn to the oceans. The Permian seas were perhaps even more vibrant than the land. They were dominated by organisms that are much less familiar to us. The great reef systems of the time were not built by the corals we know today. They were constructed by different organisms, like sponges, algae, and a group of creatures called brachiopods. Brachiopods look superficially like clams, with two shells, but they are biologically very different. In the Permian, they were far more diverse and abundant than clams and mussels are today, filling a huge variety of ecological niches. Swimming in these oceans were early sharks, bony fish, and the ammonoids, relatives of the modern nautilus with intricate coiled shells. One of the most iconic marine creatures of the Paleozoic was the trilobite, an armoured arthropod that scuttled along the seafloor. They had been around for over 250 million years, surviving previous mass extinctions, but the Permian would be their final chapter. The seafloor was also home to vast communities of crinoids, or sea lilies. These creatures look like plants with a long stalk and feathery arms, but they are actually animals, related to starfish and sea urchins. They filtered food particles from the water. In some places, the seafloor would have been a dense forest of these crinoids, swaying in the currents. This was a world in a state of relative balance. The climate was generally warm and becoming more arid, but it supported these rich, diverse ecosystems. Life had established complex relationships, intricate food webs, and nutrient cycles. This was the world that stood on the precipice. It was a world that had taken tens of millions of years to build, full of evolutionary experiments and unique forms of life, and it was all about to be systematically dismantled. When we talk about the extinction of 96% of marine species, we are talking about the end of the brachiopods, the trilobites, the sea lilies, the ancient reefs. When we talk about 70% of terrestrial species, we are talking about the fall of the gorgonopsians and the decimation of the dicynodonts. It was not just the loss of species, it was the collapse of an entire world order. Let's begin our search for evidence not with a global chemical signature, but with something more tangible, something you could, in theory, kneel down and touch. We travel to the Karoo Basin in South Africa. This region is a geological treasure trove. For over a century, paleontologists have been walking its stark, sun-baked hills and pulling the fossilized bones of Permian and Triassic animals from the rock. The layers of sedimentary rock here, ancient river floodplain deposits, provide one of the most complete records of life on land across the PT boundary anywhere in the world. Imagine you are a paleontologist walking these hills. As you move upwards through the rock layers, you are walking forward in time. In the lower layers, representing the late Permian, the world is rich. You find fossils everywhere. You might uncover the thick-boned skull of a dicynodont, its tusk still intact. A little further on, you might find the scattered skeleton of a gorgonopsian, its saber teeth gleaming in the sun. The sheer abundance and variety of fossils are staggering. For every square kilometre, you find evidence of a thriving ecosystem with many different species coexisting. There are large herbivores, small burrowing animals, and a hierarchy of predators. The world feels full. But then, as you continue to walk upward through the strata, something changes. You cross a subtle line in the rock. Geologists call this the extinction horizon, and suddenly the world becomes empty. In the layers of rock immediately above this line, the earliest Triassic, the fossils are gone. The dicynodonts, the gorgonopsians, all the large synapsids that dominated the landscape for millions of years have vanished. The rock layers that were once filled with bone are now barren. It's an eerie and profound silence written in stone. This is not a gradual fading out. It's a sharp, brutal cut-off. The paleontologists who first documented this pattern were stunned by its abruptness. They called it the zone of death. For many meters of rock, representing tens of thousands of years, there is almost nothing. The vibrant Permian ecosystem did not slowly transition into the Triassic ecosystem. It collapsed. When life does eventually reappear in the fossil record further up the rock layers, it is completely different. The new world is a disaster fauna. It is dominated by just one or two species that seem to have taken over the empty world. In the Karoo, that survivor was a creature called Lystrosaurus. It was a dicynodont, but a very hardy and perhaps generalist one. It was about the size of a pig, with a short face and two tusks. In some of the earliest Triassic rock beds, 95% of all vertebrate fossils found are Lystrosaurus. Imagine walking across an entire continent and seeing only one type of large animal. The world had gone from a rich tapestry of biodiversity to a homogeneous, depauperate landscape. This pattern, a sudden disappearance of a diverse fauna, followed by a barren interval, and then the dominance of a few disaster taxa, is not unique to the Karoo. A similar story can be found in the rock record in Russia, in China, and elsewhere. The specific species are different, but the pattern of collapse and opportunistic recovery is the same. This evidence, at the human scale of a fossil in your hand, presents us with a series of critical questions. What kind of event could cause such a rapid and profound extinction on land? It doesn't look like the result of a slow, gradual climate change. The sharpness of the boundary suggests a sudden, catastrophic trigger. What could kill off specialized apex predators like the gorgonopsians and large herbivores alike across the entire supercontinent? And what was so special about Lystrosaurus? What traits did it possess that allowed it to not only survive the apocalypse, but to thrive in its aftermath, in a world where almost everything else had died? The fossils in the Karoo don't give us the answers directly, but they define the problem with chilling clarity. They show us the crime scene. They tell us that whatever happened, it was fast, it was global, and it was devastatingly effective. The killer was not a selective one. It took the strong and the weak alike. The ground beneath our feet in this one small part of South Africa records the moment the world turned upside down. The sharp cut-off in the fossil record, that zone of death we see in the Karoo, forces us to confront the nature of the killing mechanism. What does this pattern imply about the catastrophe? Let's stress test some of the initial possibilities. Could this have been a simple case of competition, where new, better adapted species drove the old ones to extinction? The evidence speaks strongly against this. Extinction by competition is typically a slower, more piecemeal process. One species might outcompete another in a particular region, but it's unlikely to happen to dozens of major animal groups all at once across the entire globe. Furthermore, the layers of rock immediately following the extinction are not filled with new, superior competitors. They are empty. The ecological vacuum was not filled for a very long time. The world that came after was a world of ghosts. What about a more gradual environmental change, like a slow drying of the climate? This also seems inconsistent with the evidence. While the Permian climate was indeed becoming more arid, ecosystems are generally resilient to slow changes. Species can migrate, adapt, or evolve. A gradual change might cause a shift in populations or a series of smaller extinction events, but the sheer, synchronized cliff edge of the end Permian event suggests a different process. It looks less like a slow squeeze and more like a sudden hammer blow. The abruptness of the disappearance points to a stressor that exceeded the adaptive capacity of almost every living thing. This leads us to consider more catastrophic scenarios. The event had to be powerful enough to affect life on a global scale, from the plains of Pangea to the depths of the ocean. It had to be indiscriminate, affecting a wide variety of organisms in different environments. And it had to be fast, happening on a timescale of thousands of years at most, which is a mere blink in geological terms. This narrows the field of possibilities considerably. The pattern implies a profound and rapid shift in the fundamental chemistry of the planet's life support systems, the atmosphere and the oceans. It wasn't just that the climate got warmer or drier. It suggests that the very air became difficult to breathe, or the water became toxic. This is the kind of stressor that can cause a systemic collapse, rather than a gradual decline. Consider the survivors, like Lystrosaurus. What made them special? Some scientists have suggested that Lystrosaurus may have been a burrower, able to shelter underground from the harsh surface conditions. Its barrel chest and powerful limbs might suggest adaptations for digging. Perhaps it also had a unique respiratory system, better adapted to a low oxygen, high carbon dioxide atmosphere. The very existence of these disaster taxa is an important clue. They are the exceptions that prove the rule. Their survival highlights the extreme nature of the environmental filter that the extinction event imposed. Whatever happened, it selected for traits like hardiness, generalism, and perhaps the ability to tolerate toxic conditions or low oxygen. The implications of the Karoo fossil record, then, are profound. They force us to look for a causal mechanism that is not just powerful, but also rapid and global. We are searching for an event that could fundamentally poison the planet's surface environment. The quiet, empty rocks of the early Triassic are a testament to the effectiveness of this mechanism. They represent the silence after the storm, a world scrubbed clean of its former complexity. This is a critical boundary condition for any theory we propose. Any explanation for the Permian extinction must be able to account for this sudden, devastating emptiness in the rock record. It must explain how you can go from a world teeming with life to a world of ghosts, seemingly overnight. Now we move from the visible evidence of bones in the rock to the invisible evidence of chemistry. To understand what happened to the planet as a whole, we need to look at the systems that regulate its climate and life support. The most important of these is the global carbon cycle. Think of the carbon cycle as the planet's circulatory and respiratory system, all in one. Carbon is constantly moving between different reservoirs: the atmosphere, as carbon dioxide and methane; the oceans, as dissolved CO2; the biosphere, in living and dead organic matter; and the lithosphere, in rocks like limestone and in fossil fuels. For long periods, this cycle is in a rough balance. The amount of carbon entering the atmosphere from sources like volcanoes and decaying matter is roughly equal to the amount being removed by processes like photosynthesis and the burial of organic matter. This balance keeps the planet's climate relatively stable. It acts like a thermostat. Scientists can track the state of the global carbon cycle in the past by looking at carbon isotopes. Carbon comes in two main stable forms, or isotopes. The most common is carbon-12, 12C, and a slightly heavier form is carbon-13, 13C. Living organisms, particularly plants during photosynthesis, have a slight preference for the lighter carbon-12. This means that organic matter, like coal, oil, and the bodies of living things, is isotopically light. It has a lower ratio of 13C to 12C than the inorganic carbon in the atmosphere or oceans. Now, here's the key. When vast amounts of this isotopically light organic carbon are buried and turned into rock, it removes 12C from the system, leaving the remaining carbon in the atmosphere and oceans relatively enriched in the heavier 13C. Conversely, if you take a huge amount of that buried organic carbon and release it back into the atmosphere by, for example, burning massive coal deposits or releasing methane, you flood the system with light 12C. This causes the 13C to 12C ratio in the atmosphere and oceans to plummet. Geochemists can measure this ratio in ancient rocks. They look at the carbon preserved in limestone, which forms in the ocean, and it gives them a snapshot of the isotopic composition of the carbon in the seawater at that time. When they do this for rocks spanning the Permian-Triassic boundary, they find something astonishing. All around the world, in rock sections from China to Italy to Greenland, they see a massive, sharp, negative shift in the carbon isotope signature. This is called a negative carbon isotope excursion. What it means is that at the exact same time as the mass extinction event, the planet's atmosphere and oceans were flooded with a colossal amount of isotopically light carbon. The size of this excursion is one of the largest and most abrupt in the entire geological record. It is the chemical signature of a planetary catastrophe. The source of this light carbon had to be enormous. We are talking about thousands of gigatons of carbon being injected into the system in a very short period. The only plausible sources for such a massive amount of isotoporically light carbon are buried organic matter, like coal, oil, or gas, or methane trapped in permafrost or ocean sediments. This chemical fingerprint, this negative excursion, is a smoking gun. It tells us that the extinction event was not just a biological crisis. It was fundamentally a carbon cycle crisis. The planet's thermostat didn't just get nudged, it was shattered. The evidence from the carbon isotopes provides the crucial link between a potential trigger and the biological collapse. Whatever happened at the end of the Permian, it involved the release of a truly mind-boggling amount of carbon into the atmosphere. This gives us a powerful mechanism to explain the patterns we see in the fossil record. A massive injection of carbon, primarily as carbon dioxide, would have triggered a cascade of environmental effects. It's the linchpin that connects the geology to the biology. The discovery of that massive carbon isotope excursion changes everything. It moves our investigation from simply cataloguing the dead to understanding the cause of death. A sudden, massive injection of carbon into the atmosphere is not a theoretical concept. It has predictable, first-order physical and chemical consequences. Let's trace the likely chain of events, the if-then sequence that would follow such a release. If you add thousands of gigatons of carbon dioxide to the atmosphere, then the first and most direct consequence is a rapid and intense period of global warming. Carbon dioxide is a potent greenhouse gas. it traps outgoing heat. The scale of the carbon release at the end, Permian suggests a global temperature rise that would have been catastrophic. Models estimate that average global temperatures could have risen by 5 to 10 degrees Celsius, or even more. This warming would not have been uniform. The poles would have warmed much more than the equator, reducing the temperature gradient that drives ocean circulation and weather patterns. On land, this intense heat would have been devastating. Many plants and animals would have been unable to cope with the direct thermal stress. The vast, arid interior of Pangea would have become even more inhospitable, a continental-scale death valley. This direct heat stress alone could explain a significant portion of the terrestrial extinction. But the consequences don't stop there. This is a systems problem, and the feedbacks begin to kick in. As the planet warms, the oceans also warm. Warmer water holds less dissolved gas, including oxygen. So, as the seas heated up, they would have begun to suffocate. This is the beginning of ocean anoxia. This process is amplified by another feedback loop. The warming on land would have killed vast forests and other vegetation. This dead organic matter would then be washed into the rivers and eventually the oceans. As this material decayed, bacteria would consume it, and in the process, they would use up even more of the remaining oxygen in the water. So you get a vicious cycle. Warming leads to less oxygen, which leads to more die-offs, which leads to more organic decay, which leads to even less oxygen. The oceans would have stratified with a warm, oxygen-poor layer on top and stagnant, completely anoxic water below. In these anoxic conditions, a different kind of bacteria can thrive. These are sulfate-reducing bacteria. They don't breathe oxygen. They breathe sulfate, and their waste product is hydrogen sulfide, H2S. This gas is incredibly toxic to most other forms of life. As the deep ocean turned anoxic, it could have become a factory for producing hydrogen sulfide. If this toxic H2S-rich deep water were to periodically well up to the surface, a phenomenon known as an ocean burp or euxinia, it would kill almost everything in the upper ocean. It would also release poisonous hydrogen sulfide gas into the atmosphere. Some scientists have proposed a truly terrifying scenario where the atmosphere itself became poisoned by this gas, killing life on land and even damaging the ozone layer, exposing the survivors to deadly UV radiation. Simultaneously, as all that CO2 from the atmosphere dissolves in the ocean, it forms carbonic acid. This leads to ocean acidification. The water becomes more corrosive to organisms that build shells or skeletons out of calcium carbonate, like the brachiopods, crinoids, and reef builders of the Permian. Their ability to build their protective homes would be compromised, making them vulnerable and eventually leading to their collapse. So, we have a devastating cascade of second-order effects. The initial carbon injection leads to global warming. The warming leads to ocean deoxygenation and acidification. The deoxygenation can lead to the production of toxic hydrogen sulfide. Each step in this chain reaction amplifies the crisis. It explains why the extinction was so much more severe in the sea. The oceans were being attacked on multiple fronts simultaneously. They were too hot, they had too little oxygen, they were too acidic, and they may have been poisoned with hydrogen sulfide. This is the power of a systems perspective. The Permian extinction wasn't caused by global warming alone. It was caused by the total failure of the planet's life support systems, triggered by a massive perturbation to the carbon cycle. The carbon isotope signature is the key that unlocks this entire chain of devastating consequences. Let's just pause here for a moment. We've journeyed quite a distance already, from the feeling of the air in your room to the fossil beds of South Africa and the chemical signatures in ancient limestone. We've introduced some complex ideas: carbon isotopes, ocean anoxia, feedback loops. It's a lot to hold in the mind. So, just take a breath. It's a good moment to check in with where you are. What time is it where you are? Is it deep in the night, or is the sun just beginning to set? Are you in a quiet house, or moving through a busy city? This little act of grounding, of locating yourself in your own time and place, can be a useful anchor when we are navigating the deep strangeness of the past. Our minds are travelling 250 million years, but our bodies are still here now. The journey we are on together is made possible by this shared curiosity, this willingness to sit with a question and follow where it leads. If you're finding this exploration valuable, if it's sparking your own sense of wonder about our planet's long story, you might consider subscribing or leaving a quiet like. It's a simple, feather-light way to signal that these kinds of slow, methodical inquiries are worth making. It lets me know that there are others out there, in their own rooms at their own times of day, sharing in this journey. But there's no pressure. The most important thing is your attention and your curiosity. That's the real fuel for this exploration. So, let's recenter ourselves and prepare to dive back in. We have seen the evidence for the collapse, and we have a powerful mechanism, the disruption of the carbon cycle, to explain it. Now, we must turn to the prime suspect for what caused that disruption in the first place. Now we must turn our attention to the leading suspect, the most widely accepted explanation for what triggered this entire catastrophic cascade. To do this, we need to present the strongest possible case for the mainstream view. This isn't about setting up a straw man to be knocked down later. It's about giving this powerful theory the respect it deserves, because it is supported by an immense amount of evidence. This is the Siberian Traps hypothesis. Our journey takes us back to Siberia, to that vast expanse of volcanic rock we mentioned earlier. The term traps comes from the Swedish word for stairs, because the layers of lava flows often form step-like hills in the landscape, and the scale of these flows is difficult to comprehend. The Siberian Traps cover an area of over 2 million square kilometers, larger than the state of Alaska, larger than Western Europe. The total volume of erupted lava is estimated to be somewhere between 1.5 and 4 million cubic kilometers. That is enough lava to cover the entire continental United States in a layer several meters deep. This was not your typical cone-shaped volcano. This was flood basalt volcanism. Imagine fissures, hundreds of kilometers long, splitting open the earth and disgorging curtains of incandescent lava that flowed like water across the land, burying everything in their path. This was happening repeatedly in pulses for hundreds of thousands of years. The first crucial piece of evidence linking this volcanism to the extinction is timing. For a long time, dating these events with precision was difficult. But with modern radiometric dating techniques, specifically uranium-lead dating of zircon crystals found within the volcanic layers, scientists have been able to pin down the timing with remarkable accuracy. The results are clear. The main pulse of the Siberian Traps eruptions began just before the onset of the mass extinction and continued right through it. The correlation in time is almost perfect. The volcanism starts, the carbon cycle goes haywire, and the biosphere collapses. This close temporal link is the cornerstone of the hypothesis. But the lava itself wasn't the main killing mechanism. The real weapon was gas. The magma that fed these eruptions did not just erupt onto the surface. As it moved up through the Earth's crust, this colossal body of molten rock, which is called a large igneous province, or LEP, acted like a giant stove burner. The crust in this part of Siberia was not just inert rock. It was full of huge deposits of coal, oil, natural gas, and carbonate rocks. As the magma intruded into these layers, it essentially cooked them, releasing their stored carbon directly into the atmosphere. This is a crucial part of the story. The eruptions themselves released a lot of CO2, but the real catastrophe came from the magma igniting the vast fossil fuel reserves of the Siberian basin. This explains the carbon isotope signature perfectly. The burning of coal and the release of methane would flood the atmosphere with exactly the kind of isotopically light carbon that we see in the geological record. It provides a neat and powerful explanation for the primary chemical fingerprint of the extinction. Further evidence comes from other chemical traces found in rocks at the PT boundary around the world. Geochemists have found spikes in elements like nickel and other metals that are characteristic of emissions from this type of volcanism. They have also found chemical evidence of widespread wildfires in the form of soot and charcoal layers, which could have been ignited by the hot lava flows or the intense heat. There's also evidence for massive releases of sulfur dioxide and halogen gases, which would have created intense acid rain, devastating forests on land and further altering ocean chemistry. So, the case against the Siberian Traps is formidable. You have a cataclysmic event of the right scale, one of the largest volcanic episodes in the last 500 million years. You have the right timing. It happens at exactly the same time as the extinction. And you have the right mechanism. It provides a source for the massive isotopically light carbon injection that we know occurred, along with other chemical poisons like acid rain. It elegantly connects all the major pieces of evidence. The volcanism in Siberia provides the trigger that disrupts the carbon cycle, which in turn leads to the global warming, ocean anoxia, and acidification that we see recorded in the rocks and fossils worldwide. This is why it is the leading hypothesis. It is a comprehensive, evidence-based explanation that accounts for the widest range of observations. While the Siberian traps hypothesis is powerful and widely supported, it is not the only explanation that has been proposed. It's important to explore these alternatives, not necessarily as equal contenders, but as a way to test the completeness of the mainstream theory and to acknowledge the aspects of the extinction that are still not fully understood. We can present these side by side with the volcanic model to see where they differ. One of the most long-standing alternative ideas is an asteroid or comet impact similar to the one that killed the dinosaurs 66 million years ago. The appeal of this hypothesis is that an impact is the ultimate sudden catastrophe. It could certainly trigger a global collapse. Proponents of this idea have searched for the telltale signs of an impact: a crater of the right age, a layer of iridium, an element rare on Earth, but more common in asteroids, at the PT boundary, and shocked quartz, mineral grains deformed by intense pressure. The evidence here is much more ambiguous than for the dinosaur extinction. Some researchers have reported finding shocked quartz and other impact-related markers in PT boundary layers in Antarctica and Australia. There are also candidate craters, such as the Badut feature off the coast of Australia, but their age and origin as impact structures are highly debated within the scientific community. There is no globally recognized iridium layer like the one at the Cretaceous-Paleogene boundary. So, while an impact cannot be completely ruled out, perhaps it was a contributing factor, or perhaps we just haven't found the smoking gun yet, it lacks the strong, consistent, worldwide evidence that supports the volcanic hypothesis. The impact theory stands in contrast to the Siberian traps model primarily in its timing and mechanism. An impact is a near instantaneous event, while the volcanism, though rapid, was spread out over tens or hundreds of thousands of years. Another important alternative hypothesis focuses on a different source for the isotopically light carbon: methane. There are vast quantities of methane trapped in a frozen, ice-like state in cold, deep ocean sediments and permafrost. These are called methane clathrates or methane hydrates. Methane is an even more potent greenhouse gas than carbon dioxide, especially over short timescales. The idea is that the initial warming from the Siberian traps could have acted as a trigger, warming the oceans and permafrost just enough to destabilize these clathrates. This would lead to a massive release of methane into the atmosphere, causing a runaway feedback loop of even more intense warming. This is often called the methane burp hypothesis. This model is not mutually exclusive with the Siberian traps theory. In fact, many researchers now see it as a likely amplifier. The volcanism provided the initial push, and the subsequent methane release tipped the system over the edge. The main challenge here is finding direct evidence. It is very difficult to distinguish in the rock record between carbon that came from methane and carbon that came from CO2 released by cooking coal beds. Both are isotopically light. The debate here is about the relative contribution of each source. A more radical idea shifts the blame from geology to biology. This hypothesis suggests that the key event was the evolution of a new type of microbe. Specifically, a genus of archaea called Methanos arsina developed a new metabolic pathway that allowed it to efficiently consume organic matter in marine sediments and produce methane as a waste product. The theory proposes that a horizontal gene transfer from another bacterium gave Methanos arsina this new superpower, and their population exploded in the Permian oceans. This microbial bloom would have released enormous quantities of methane, triggering the climate catastrophe. Evidence for this includes the fact that the genetic machinery for this pathway appears to have evolved around this time, and the bloom would have required large amounts of nickel, an element that, as we saw, was being supplied in abundance by the Siberian traps volcanoes. In this view, the volcanoes are not the direct cause of the carbon release, but rather the catalyst that fertilized the microbial apocalypse. Each of these alternatives highlights a different aspect of the Earth system. the vulnerability of the planet to extraterrestrial impacts, the potential for runaway climate feedbacks, and the power of microbial evolution to reshape the entire biosphere. While the Siberian Traps remains the central pillar of our understanding, it is likely that the full story of the Permian extinction involves a complex interplay of these factors. A perfect storm where volcanism, climate feedbacks, and perhaps even biology conspired to create the greatest catastrophe life has ever known. How do we know what we think we know? This is a crucial question in any scientific inquiry, but it becomes especially pointed when we are dealing with the deep past. Our entire reconstruction of the Permian world is built upon a foundation of data extracted from ancient rocks, and it's essential to understand the limitations of those methods. We are detectives arriving at a crime scene 252 million years after the fact, and much of the evidence has been degraded, altered, or erased entirely. Our primary tool for understanding the sequence of events is stratigraphy, the study of rock layers. The principle is simple. In an undisturbed sequence of rocks, the oldest layers are at the bottom and the youngest are at the top. But the rock record is not a perfect book. There are missing pages. A period of erosion can scrub away millions of years of history from a location. Geologists call this an unconformity. Finding a location with a complete, uninterrupted sequence of sediment across the PT boundary is incredibly rare. This is why sites like the Karoo Basin or the sections in Meishan, China, are so important. They are among the most complete records we have. Even in these places, the rate of sedimentation can change, which can stretch or compress time in the rock record, making it difficult to judge the true duration of events. Our dating methods have also evolved. Early paleontologists could only provide relative dates. This fossil is older than that one. But the development of radiometric dating has allowed us to assign absolute ages to certain layers. This is typically done by measuring the decay of radioactive isotopes like uranium turning into lead within crystals like zircon found in volcanic ash beds. These ash beds are like time stamps in the rock record. The precision of these dates has become astonishing, allowing us to say that the extinction happened 252.28 million years ago, plus or minus a few tens of thousands of years. But these high-precision dates are only available for the rare layers that contain these specific minerals. We have to extrapolate between these anchor points. Then there is the challenge of survivorship bias. The fossil record is profoundly incomplete. Only a tiny fraction of the organisms that have ever lived were preserved as fossils, and of those only a tiny fraction have been discovered. Soft-bodied organisms rarely fossilize. Organisms that lived in upland environments, where erosion is dominant, are much less likely to be preserved than those that lived in sedimentary basins. This means our picture of the Permian biosphere is inherently biased towards creatures with hard parts that lived in the right kinds of places. There is also a famous paleontological bias known as the Signor-Lipps effect. This effect states that, because the fossil record is incomplete, the last known fossil of a species will almost certainly predate the actual time that species went extinct. This can have the effect of making a sudden, catastrophic extinction appear more gradual in the rock record than it actually was. The rarer a species is, the more likely it is to seem to disappear from the record long before the actual extinction event. Paleontologists are aware of this and use statistical methods to try to correct for it, but it remains a fundamental challenge. Our chemical proxies also have their limitations. When we measure carbon isotopes in a rock, we have to be sure that the chemical signature we are reading is the original, primary signal from the Permian Ocean, and not something that has been altered by millions of years of heat, pressure, and chemical reactions during burial. Geochemists have developed rigorous tests to screen for this alteration, but it's a constant concern. We are listening for a very faint whisper from the past, and we have to be sure we are not just hearing the noise of subsequent geological processes. So, we must hold our beautiful, complex models of the Permian world with a degree of humility. They are built on incomplete data, using imperfect tools, but this is not a reason for despair. It is the engine of science. Every limitation, every uncertainty points the way to new research. It prompts us to search for more complete rock sections, to develop more precise dating techniques, and to refine our understanding of how chemical proxies work. Our knowledge is provisional, but it is constantly improving, as we learn to read the faint and fractured language of the rocks with ever-increasing clarity. With these methodological caveats in mind, let's return to our central thread, the cascade of events triggered by that colossal carbon release. The words we use to describe the past are not neutral. They shape our thinking, often in subtle ways. When we talk about the Earth system, especially during a crisis like the Permian extinction, it's easy to fall into the trap of using anthropomorphic language. We might say the planet was sick, that the oceans were angry, or that life fought back. These metaphors can be evocative, but they can also be misleading. The Earth is not a conscious organism with intentions or emotions. It is a complex physical and chemical system governed by feedback loops. The oceans didn't decide to become anoxic. Rather, a set of physical conditions, increased temperature, increased nutrient runoff, led to a predictable chemical outcome. The process was automatic, not intentional. It's more accurate to think of it like a piece of machinery or a complex computer program. If you change a critical parameter, the system's output will change according to the rules of its operation. Using this more mechanistic language helps us maintain clarity in our thinking. Instead of saying the biosphere collapsed, which can imply a single monolithic event, it's more precise to say that the rate of extinction dramatically exceeded the rate of speciation and that primary productivity plummeted. Instead of saying the planet tried to heal itself, we can say that after the initial perturbation, negative feedback loops, like the weathering of silicate rocks drawing down CO2, gradually returned the system to a new, more stable state over millions of years. This isn't just semantic pedantry. The choice of language frames our inferences. If we think of the Earth as a superorganism, we might be tempted to look for purpose or design in its behavior. If we think of it as a complex, nonlinear system, we are more likely to look for thresholds, tipping points, and feedback mechanisms. The latter framing has proven to be a much more powerful and predictive way to understand planetary science. We also need to be careful with the limits of our metaphors. We've used the analogy of a thermostat to describe the carbon cycle. This is a useful starting point. A thermostat is a negative feedback system. When it gets too hot, the cooling turns on. When it gets too cool, the heating turns on. The Earth has similar long-term stabilizing feedbacks. But the thermostat analogy can break down. A planetary system is vastly more complex. It has multiple interacting feedback loops, some positive, destabilizing, and some negative, stabilizing. During the end Permian, a massive initial shock seems to have overwhelmed the negative feedbacks and triggered a series of powerful positive feedbacks. Warming, causing methane release, causing more warming, that pushed the system far from its stable state. The thermostat didn't just get turned up, it broke and was rewired to make things hotter. The same care is needed when we talk about evolution during the recovery. It's tempting to describe the survivors like Lystrosaurus as winners. But they didn't win a competition in the traditional sense. They simply happened to possess a set of traits that allowed them to tolerate a set of environmental conditions that 90% of their neighbors could not. They were lucky survivors, not champions. Their success was a matter of contingency, not inherent superiority. By being mindful of our language, by choosing words that reflect mechanism rather than intent, and by constantly questioning the limits of our analogies, we can build a more accurate and nuanced model of the Permian world. We can avoid telling stories about the past that are more reflective of our own human psychology than of the underlying planetary processes. The Earth system is not a character in a drama. It is the stage, the script, and the laws of physics, all at once. Let's make this more concrete. Let's walk through the chain of causality, applying the evidence we've discussed so far. Imagine you are a single organism, a gorgonopsian, living on the plains of central Pangea in the final millennium of the Permian. What does the world feel like as it begins to unravel? For most of your life, the world has been predictable. The seasons, though harsh, follow a pattern. The herds of dicynodonts you prey upon are plentiful. The air is breathable. But then, things begin to change, subtly at first. On the other side of the world, in Siberia, the flood basalts have begun to pour forth. The initial pulse of eruptions releases immense clouds of sulfur dioxide into the stratosphere. This actually has a cooling effect, creating a volcanic winter that might last for a few years or a decade. You experience this as a series of unusually cold, dark years. The plants struggle, and the herbivores you hunt become weaker and less numerous. This initial cooling shock places the ecosystem under stress, but this effect is temporary. The sulfur dioxide soon rains out of the atmosphere as acid rain. This acid rain damages the forests, stripping nutrients from the soil and poisoning the rivers. The leaves of the glossopterid trees become yellow and withered. The water in the streams you drink from becomes sour. Now, the main event begins. The magma intruding beneath Siberia starts to cook the vast coal basins, releasing truly colossal amounts of carbon dioxide into the atmosphere. This is the signal that geochemists will one day read in the carbon isotope record. For you, this is not an abstract number. You feel it as a relentless, suffocating rise in temperature, year after year, decade after decade. The brief volcanic winter is replaced by a runaway greenhouse summer. The average temperature climbs by 5, then 6, then 7 degrees. The heat is oppressive and inescapable. The rivers and water holes you depend on begin to dry up. The plant life, already stressed by acid rain, begins to die off on a massive scale due to the heat and drought. The dicynodont herds collapse, not just from lack of water, but from outright starvation. As you search for prey, you find only carcasses. The air itself is changing. The CO2 levels are rising, and as the global biosphere collapses, oxygen levels begin to fall. Your breathing becomes labored. Every hunt leaves you more exhausted than the last. You are living in a world that is simultaneously starving and suffocating you. The stress is physiological and relentless. Your species, the mighty Gorgonopsians, are apex predators, finely tuned to a specific set of environmental conditions. But your adaptations, speed, power, saber teeth, are useless in this new world. You cannot eat heat. You cannot drink dust. You cannot fight a change in the composition of the air itself. One by one, your kind perishes, not from a single dramatic blow, but from 1,000 cuts. Starvation, dehydration, heat stroke, anoxia. Your body, the product of millions of years of evolution, is simply not equipped to handle a world that has changed so much, so fast. The last of your kind finds a shaded rock overhang, seeking refuge from the baking sun. You lie down, your breathing shallow, and you close your eyes on a world that has become a furnace. Your death is a single data point in a global pattern of extinction. Your bones will be buried by the wind-blown dust of the new, empty world, and millions of years later, a paleontologist will find your fossilized skull and wonder what kind of world you inhabited and what terrible fate befell you. This is how the evidence at a human scale, the disappearance of a fossil from a rock layer, connects to the planetary scale mechanism. Now, let's shift our perspective. Let's zoom out from the experience of a single animal and look at the planet as an interconnected system, applying our understanding of feedbacks and thresholds. We are moving from a narrative scale to a systems dynamic scale. Let's start with the baseline state, the late Permian Earth. It's a world with one supercontinent, Pangea. This geography creates a climate system that is already prone to extremes. The vast interior is arid, and the ocean circulation patterns are different from today's. The carbon cycle is in a state of relative equilibrium, with atmospheric CO2 levels that are high by modern standards but stable. Let's quantify this. Before the event, CO2 might have been around 1,000 parts per million, ppm, compared to just over 400 ppm today. Now, we introduce the initial perturbation, the Siberian traps. Let's focus on the carbon release. We can model this as an injection of carbon into the atmospheric reservoir. The evidence from the isotope excursion suggests a release of somewhere between 5,000 and 10,000 gigatons of carbon over a period of tens of thousands of years. Let's take a conservative number, an average injection rate of 0.5 gigatons of carbon per year. For comparison, modern human emissions are around 10 gigatons per year, but the Permian event sustained this high rate for a geologically significant period. This injection immediately begins to overwhelm the Earth's natural carbon sinks. The ocean is the primary sink, but it can only absorb CO2 so fast. As CO2 levels in the atmosphere rise, global temperatures increase due to the greenhouse effect. A simple energy balance model would suggest that doubling CO2 leads to about 3 degrees Celsius of warming. This is the climate sensitivity. With the amount of CO2 being added, a temperature rise of 8 to 10 degrees Celsius is entirely plausible. Now, the feedback loops kick in. This is where the system's behavior becomes nonlinear. Feedback loop number 1, the ice albedo feedback. The Permian world had polar ice caps. As the planet warms, these ice caps begin to melt. Ice is bright and reflective, high albedo, reflecting sunlight back into space. Open water or land is dark and absorbent, low albedo. As the ice melts, the Earth's surface becomes darker, absorbs more solar energy, and warms up even more, which melts more ice. This is a powerful positive or amplifying feedback. Feedback loop number 2, the methane clathrate feedback. As we discussed, the initial warming from the CO2 penetrates the oceans. When the deep ocean waters warm by a few degrees, they can cross a threshold where the frozen methane clathrates on the seafloor become unstable. They turn from a solid to a gas, releasing vast quantities of methane. Methane is a greenhouse gas that is approximately 25 times more potent than CO2 over a 100-year timescale. This adds another, even more powerful warming agent to the atmosphere, kicking the temperature rise into an even higher gear. This is another strong positive feedback. Feedback loop number 3, the terrestrial biosphere feedback. On land, the combined stress of acid rain, heat and drought causes a massive dieback of forests. Trees are a huge reservoir of carbon. When they die and decompose, or burn in wildfires, they release that stored carbon back into the atmosphere as CO2. Furthermore, a dead forest is no longer pulling CO2 out of the atmosphere through photosynthesis. So, a crucial carbon sink is turned into a carbon source. This is a third positive feedback. What we see here is a system pushed past a tipping point. The initial shock from the volcanoes was large, but its effects were magnified enormously by these internal feedback mechanisms. The planet's own operating system began to work against itself, accelerating the shift to a new, much hotter and more hostile state. The oceans responded in turn. The warming reduced oxygen solubility. The collapse of the marine biosphere meant less photosynthesis in the surface waters, which is a major source of oceanic oxygen. The influx of nutrients from the dying landmasses fueled bacterial blooms that consumed the remaining oxygen. The system tipped into a state of widespread anoxia. This is a classic example of a threshold effect in a complex system. For a long time, the system can absorb disturbances, but once a certain threshold is crossed, it rapidly transitions to a new state from which it is very difficult to return. The Permian extinction shows us a planet crossing that threshold. Our investigation so far has been confined to the Earth itself. But our planet is not an isolated system. It exists in a cosmic context, locked in an intricate dance with its nearest neighbour, the Moon. Let's take a moment to consider this larger coupling, not as a direct cause of the extinction, but as an archetype for the kind of long-term stabilizing forces that shape a planet's habitability over geological timescales. The relationship between a planet and its moon can have profound effects on the planet's long-term stability. One of the most critical is the stabilization of the planet's axial tilt, or obliquity. The Earth is tilted on its axis by about 23.5 degrees relative to its orbital plane. This tilt is what gives us our seasons. Without our large moon, the gravitational nudges from other planets, particularly Jupiter, would cause the Earth's axial tilt to vary chaotically over millions of years. It might swing from 0 degrees, no seasons, to as much as 85 degrees, extreme seasons where the poles point almost directly at the sun. Such wild swings in obliquity would lead to dramatic and unpredictable climate shifts, making it much harder for complex life to gain a permanent foothold. The Moon acts as a giant gravitational anchor, a gyroscopic stabilizer, damping these oscillations and keeping the Earth's tilt within a relatively narrow, stable range. This has provided our planet with a degree of long-term climate stability that it might otherwise lack. There is another, even slower process at play: tidal friction. The Moon's gravity pulls on the Earth, creating the ocean tides. As the Earth rotates, this tidal bulge is dragged across the ocean floor, creating friction. This friction acts as a brake on the Earth's rotation, causing the length of the day to gradually increase over geological time. The energy lost from the Earth's spin is transferred to the Moon's orbit, causing it to slowly move further away from the Earth, at a rate of about 3.8 centimeters per year. We can wind this clock backward. In the deep past, the Moon was closer, and the Earth was spinning faster. A day in the late Permian was not 24 hours long, it was closer to 22 hours. The Moon would have appeared larger in the sky, and the tides would have been stronger. While these changes are slow, they are a fundamental part of the planet's long-term evolution. They form the deep background rhythm against which events like the Permian extinction play out. The Earth-Moon system is a coupled harmonic oscillator. Its long-term stability provides a kind of predictable canvas. This concept of planetary-scale coupling and damping is a useful mental model. It helps us think about the different timescales of stability. On the scale of hundreds of millions of years, the Moon provides a kind of stabilizing architecture for the climate system. But this long-term stability does not preclude short-term catastrophic instability. The Permian extinction shows us that even within a broadly stable architectural framework, a sufficiently large internal shock can still trigger a runaway system failure. The presence of the Moon could not save the Earth from the consequences of the Siberian traps. It's like having a well-designed, stable house that is still vulnerable to a massive fire starting in the basement. The architecture provides resilience against certain kinds of disturbances, external gravitational perturbations, but not others, massive internal greenhouse gas releases. Thinking about the Earth-Moon coupling reminds us to consider the nested hierarchies of time and stability. The Permian extinction was a crisis that unfolded over tens of thousands of years, a violent spasm within a planetary system that has been broadly stable for billions of years. It highlights the difference between the background conditions that make a planet habitable in the first place, and the contingent events that can threaten that habitability from within. What are the consequences of this long-term planetary coupling for habitability? How does the presence of a large moon providing that gyroscopic stability translate into the lived experience of life over geological time? The answer lies in the concept of predictability. A stable axial tilt means a predictable pattern of seasons. Year after year, millennium after millennium, the general pattern of solar energy distribution across the planet's surface remains the same. This predictability is a cornerstone of long-term evolution. It allows life to develop complex life cycles that are synchronized with the seasons. Think of trees dropping their leaves in winter, animals migrating or hibernating, the timing of reproductive cycles. These are all biological adaptations to a reliable and repeating environmental rhythm. In a world with a chaotically varying axial tilt, this kind of long-term evolutionary tuning would be impossible. A region that for 10,000 years had mild seasons could suddenly be plunged into a regime of extreme seasonal swings for the next 20,000 years, with the sun beating down on one pole for half the year and leaving the other in frozen darkness. Ecosystems would be constantly scrambled, unable to establish the kind of deep, co-evolved complexity that we see in our own world's history. So, the first implication is that the Moon's stabilizing influence has provided a long-term climatic framework that is gentle enough for complex life to flourish and specialize. It smoothed out the highs and lows of climatic variation, creating a more forgiving canvas for evolution to paint on. The gradual slowing of the Earth's rotation also has consequences. A faster spinning planet in the Permian meant a stronger Coriolis effect. This would have influenced weather patterns, creating more numerous and perhaps more tightly wound storm systems. The winds would have been stronger. The difference between a 22-hour day and a 24-hour day might seem small, but over an entire planet, it changes the fundamental dynamics of the atmosphere and oceans. The stronger tides from a closer moon would have also had significant ecological effects. The intertidal zone, the area of the shoreline exposed between high and low tide, would have been much larger. This creates a unique and challenging environment, and it's thought to be a critical zone for evolutionary innovation, perhaps even for the transition of life from water to land much earlier in the Paleozoic. These long, slow changes in the planetary environment, the lengthening of the day, the receding of the moon, the steadying of the seasons, form the deep, slow drumbeat of Earth's history. They are the background conditions. The Permian extinction, in contrast, was a sudden, cacophonous noise, a cymbal crash that momentarily drowned out the underlying rhythm. This helps us understand what makes events like the Great Dying so devastating. Life is incredibly adaptable to slow, predictable change. Evolution can keep pace with the gradual lengthening of the day, but it is profoundly vulnerable to rapid, chaotic change that exceeds its adaptive capacity. The Permian extinction was a crisis because its timescale, tens of thousands of years, was far too fast for the normal processes of evolution to respond. The environmental changes outpaced the ability of organisms to adapt. This contrast between slow, stable planetary evolution and rapid, catastrophic environmental shock is fundamental. The planetary habitability provided by factors like the Moon is not a guarantee of safety. It is a background condition that makes complex life possible, but it does not make it indestructible. The system is robust, but it is not infinitely resilient. It has breaking points. The Permian extinction was the moment the system found its breaking point. To read the story of the past, we need to find its archives. We need to find places where the planet has recorded its own history. The most important of these archives are layers of sedimentary rock. Think of a deep lake or a quiet ocean basin. Year after year, particles of mud, sand, and the remains of living organisms drift down and settle on the bottom. Each layer is a snapshot of a moment in time. A thick sequence of these layers is like a book, with the oldest pages at the bottom. Geologists drill deep cores into these sediments, pulling up long cylinders of rock that allow them to read this history. The rock itself tells a story. A layer of coarse sandstone might indicate a fast-moving river, while a layer of fine-grained shale suggests a calm, deep-water environment. A layer of coal is the remnant of a lush, buried swamp. But hidden within these layers is an even richer archive, the chemical and biological signals they contain. These are the lagging indicators, the echoes of past events. As we've discussed, the isotopic composition of the rock can tell us about the global carbon cycle and past temperatures. But there are other clues. Scientists can also look for biomarkers. These are complex organic molecules that are produced by specific types of living organisms and are stable enough to be preserved for millions of years. For example, certain molecules called isorenieratinae are produced by green sulfur bacteria. These bacteria are unique. They are photosynthetic, but they cannot tolerate oxygen and require both light and hydrogen sulfide to live. Finding a spike of these specific biomarkers in sedimentary rocks from the PT boundary is a powerful piece of evidence. It tells us that at that time the photic zone, the upper layer of the ocean where light can penetrate, was both anoxic, no oxygen, and euxinic, containing hydrogen sulfide. This is a direct chemical fingerprint of the toxic H2S-rich ocean we discussed earlier. It's a clue that confirms our model of what the oceans were like. Another type of archive is the fossil record of pollen and spores. Plants produce enormous quantities of these tiny, durable particles. They get blown by the wind and settle in sediments, creating a detailed record of the vegetation in a particular region. Across the PT boundary, palynologists, scientists who study pollen and spores, see a dramatic shift. The diverse pollen assemblages of the late Permian, representing complex forests, are suddenly replaced by layers that are almost entirely dominated by fungal spores. This fungal spike is found all over the world. What does it mean? It suggests a world where the forests have died on a massive scale. The fungi are the decomposers, feasting on the immense amount of deadwood left behind. It's the signature of a dead or dying terrestrial ecosystem, a world of rot. These archives, the sediments, the isotopes, the biomarkers, the pollen, are our primary sources of information. They are like planetary memory. But it's important to remember that memory can be imperfect. The archives are often incomplete, and the signals can be faint. Reading them requires incredible scientific ingenuity. We are taking a tiny sample of rock, crushing it into a powder, putting it into a mass spectrometer, and from the ratios of atoms within it, we are reconstructing the temperature and chemistry of an ocean that vanished 250 million years ago. It is a testament to the power of the scientific method that we can do this at all. These archives don't give us a perfect movie of the past, but they provide us with a series of crucial still frames. And by piecing those frames together from archives all over the world, we can begin to build a coherent story of how the planet's systems unraveled. Given that our knowledge is derived from these lagging indicators in the geological archive, what are the constraints on what we can infer? What can we say with high confidence, and where do we have to be more cautious? We can be very confident about the big picture. The evidence for a massive, rapid and global mass extinction event at the end of the Permian is overwhelming. The fossil record in numerous locations shows this clearly. We can also be very confident that this event was associated with a profound disruption of the global carbon cycle. The negative carbon isotope excursion is a global signal, found in dozens of locations, in both marine and terrestrial rock sections. Its magnitude and abruptness are well established. This tells us, with high certainty, that a huge amount of light carbon was released into the atmosphere and oceans. Similarly, we can be confident that the world experienced a significant warming event. The oxygen isotope data, though sometimes complex to interpret, points consistently to a major temperature increase. The physical consequences of this warming, such as ocean anoxia, are also strongly supported by widespread geological evidence, including the presence of finely laminated black shales, which can only form in the absence of oxygen and burrowing organisms, and the chemical biomarkers for anoxic conditions. The connection between the extinction and the Siberian Traps volcanism is also very strong, primarily due to the precise and robust dating that shows the two events were simultaneous. However, when we move from the what to the how fast and in what order, our confidence levels become lower. The exact duration of the main extinction pulse is still a subject of active research and debate. Was it 100,000 years? 60,000 years? Even shorter? The resolution of the rock record makes it very difficult to pinpoint the duration with absolute certainty. Different studies in different locations can yield slightly different answers, and reconciling them is a major challenge. The precise sequence of events is also debated. Did the terrestrial collapse happen before, after, or at the same time as the marine collapse? Did the ocean acidification precede the anoxia, or did they happen together? The archives can sometimes give us seemingly contradictory signals. For example, some records suggest that the terrestrial ecosystems were under stress well before the main marine extinction pulse. This could mean the effects of the Siberian traps, like acid rain, hit the land first. Untangling this precise timeline is at the cutting edge of PT boundary research. The exact contribution of different carbon sources, volcanic CO2, baked coal, methane hydrates, is also an area of uncertainty. While we know a massive amount of light carbon was released, portioning out the blame between these different sources is difficult. Scientists use complex models to try to figure out which combination of sources best fits the isotopic data, but these are models, not direct measurements. These uncertainties are not failures of the science. They are the markers of a healthy and active field of research. They are the puzzles that future generations of geologists and paleontologists will work to solve. So, what we have is a picture that is sharp in its broad outlines, but becomes fuzzier as we zoom in on the details. We can think of it in terms of confidence bands. We have very high confidence in the link between volcanism, carbon release, global warming, and mass extinction. We have moderate to high confidence in the role of ocean anoxia and acidification as key killing mechanisms. We have a lower confidence and a more active debate about the exact timing, tempo, and precise sequencing of the different aspects of the collapse. It's like knowing the cause of a house fire was an electrical fault in the basement, but still debating which specific wire shorted out first and how fast the flames spread to the upper floors. We have followed several threads of evidence, from the fossils in the Karoo to the chemical whispers in ancient mud. We've seen how a volcanic eruption in Siberia could trigger a global climate catastrophe, amplified by the Earth's own feedback systems. We have a trigger, a mechanism, and a devastating result. Before we go further, let's just flag where we are heading. We are about to move from the geological and chemical evidence to the biological systems themselves. How do entire ecosystems, entire biomes interact with the planetary systems around them? How does life itself shape its own environment? We will soon explore the conversations that happen between vast forests and the atmosphere, and how the collapse of those conversations contributed to the crisis. We will also need to re-examine the geography of the Permian world, that strange supercontinent of Pangea, and ask how its unique configuration made the entire global system more fragile. This will help us synthesize the pieces we've already assembled into a more complete and dynamic picture of the world on the brink. We are moving from the physics and chemistry of the collapse to its deep biology and geography. This synthesis will be a key part of our journey, bringing together the different lines of evidence into a more holistic understanding. For now, just keep in mind that the story is not just about a volcano and an ocean. It's about a living world's response to an unprecedented shock. Let's zoom in on the living components of the Earth system. It's easy to think of life as a passive victim of geological and chemical events, but the biosphere is also an active participant in shaping the planet's environment. There are constant conversations, in the language of chemistry and energy, between the world's biomes and the atmosphere. Consider a large forest. It's not just a collection of trees sitting on the land, it's a powerful biogeochemical engine. Through photosynthesis, it inhales vast quantities of carbon dioxide from the atmosphere, using the carbon to build its own tissues and exhaling oxygen as a waste product. A mature forest is a massive carbon sink, locking away atmospheric carbon for centuries. But the conversation is more complex than that. Trees also release a variety of volatile organic compounds, VOCs, into the air. These molecules can act as condensation nuclei, particles around which water vapor can gather to form clouds. In this way, a forest can literally make its own rain. It creates a local climate that is more humid and cooler than it would otherwise be. This is a feedback loop. The forest needs rain, and by its own metabolic processes, it helps to create the conditions for that rain. This process is called moisture recycling. A water molecule might be evaporated from the ocean, fall as rain on the coast, be taken up by a tree, transpired back into the atmosphere, and then carried further inland to fall as rain again. A large, contiguous forest can move moisture deep into the interior of a continent this way. Now, imagine what happens when you dismantle this system during the end Permian. The initial stress from acid rain and heat begins to kill the great glossopterid forests. As the trees die, several things happen at once. First, the massive carbon sink vanishes. Worse, as the dead trees decay or burn, the forest becomes a massive carbon source, releasing its stored carbon back to the atmosphere and amplifying the initial warming, a feedback we've already touched upon. Second, the moisture recycling system breaks down. With the trees gone, the interior of the continent becomes much drier. The death of the forest accelerates the process of desertification. This creates another feedback loop. Drought kills trees, and dead trees lead to more intense and widespread drought. Third, the physical structure of the soil collapses. The roots of the trees hold the soil together. When the trees die, the soil is exposed to the elements. The intensified wind and rain of the disrupted climate system would strip this soil away, a process called sheet erosion. The landscape is denuded, and all of that soil, rich in organic matter and nutrients, is washed into the rivers and carried out to sea. This sudden, massive influx of nutrients from the land into the coastal oceans has its own devastating effect. It causes huge blooms of algae and bacteria near the surface. When these blooms die and sink, their decomposition consumes all the available oxygen, creating the dead zones and anoxic conditions that we know were so widespread. So we see a cascade of failure that begins on land and propagates into the ocean. The death of the forests is not just a consequence of the climate crisis, it is an active participant in accelerating and amplifying it. The biome-atmosphere conversation, which for millions of years had been a stabilizing one, was suddenly turned into a destabilizing, runaway process. This is a critical insight. It shows that the biological and geological components of the Earth system are deeply coupled. You cannot break one without profoundly affecting the other. The Permian extinction was not just a geological event that life had to endure, it was a biogeochemical catastrophe where the collapse of the biosphere fed back to make the physical, environmental changes even worse. The silence of the dead forests on Pangea had a powerful and deadly echo in the suffocating oceans. The story of the biome-atmosphere conversation breakdown reveals a fundamental truth about complex systems. Their resilience has limits. Ecosystems are not infinitely adaptable. They have thresholds, tipping points beyond which they cannot maintain their structure and function. For millions of years, the Permian forests were resilient. They could handle normal droughts, storms, and fires. They had evolved mechanisms to cope with a certain range of environmental variability. A small fire might clear a patch of forest, but it would be recolonized. A moderate drought might kill some trees, but the ecosystem as a whole would survive. These systems are stabilized by a web of negative feedback loops. But the assault at the end of the Permian was not a normal disturbance. It was a multi-pronged attack that pushed the system beyond its breaking point. The stress of intense acid rain, followed by a rapid and extreme temperature rise, was a combination that the ecosystem had no evolutionary preparation for. The disturbance was too large, too fast, and too novel. It crossed a critical threshold. Once this threshold was crossed, the system's behavior flipped. The stabilizing negative feedbacks were overwhelmed by destabilizing positive feedbacks. The death of a few trees made conditions worse for their neighbors, leading to the death of more trees and so on in a runaway cascade. The forest ecosystem didn't just shrink, it collapsed. The failure mode was not graceful. It was a rapid, wholesale unraveling. This concept of thresholds and nonlinear collapse is crucial for understanding mass extinctions. It explains why the environmental changes could be so dramatic and so abrupt. The Earth system wasn't just gradually getting warmer, it was being pushed into a completely new, hostile state from which it couldn't easily return. The recovery from such a collapse is a long and difficult process. You can't just regrow a forest overnight. First, you need to re-establish a stable soil layer, which can take centuries or millennia. You need the climate to stabilize, and you need survivor species that can act as pioneers, colonizing the barren landscape. The long, dead zone in the fossil record after the extinction reflects this slow, painful process of rebuilding. The planet's life support systems had to be constructed again, almost from scratch. This perspective also gives us a new way to think about resilience. Resilience is not about being unchanging or invulnerable. It's about the ability of a system to absorb disturbance and reorganize while retaining its essential function. The Permian ecosystems had resilience, but the Permian extinction event was a shock that exceeded their capacity to absorb and reorganize. The system broke. It highlights the difference between robustness and fragility. A system can seem incredibly robust for a long time, weathering all sorts of smaller shocks. But if it has a critical vulnerability, a hidden threshold, a sufficiently large or novel shock can trigger a surprisingly rapid and complete failure. The Permian extinction was the moment when the hidden fragilities of the Pangean world were brutally exposed. It demonstrates that the stability of the biosphere is not guaranteed. It is a contingent property of a complex system operating within a certain range of conditions. Push it outside that range, and it can fail in spectacular and terrifying ways. Let's try an analogy to help us think about the biological resilience and failure we've been discussing. We have to be very careful with analogies, as we've said, but they can be useful tools for thought. Imagine the entire Permian biosphere as a complex computer operating system. Let's call it BioOS 1.0. This operating system has been developed and debugged over hundreds of millions of years of evolution. It's not perfect, but it's incredibly robust. It has millions of lines of code, the genetic information in all the different species. This code has been tested against all sorts of inputs: climate fluctuations, volcanic eruptions, the evolution of new predators. The system has built-in redundancy. If one application, a particular species, crashes, the whole system doesn't go down. Other species can fill the niche. It has error correction routines. Ecosystems can recover from fires and storms. It has complex feedback mechanisms that regulate the flow of energy and nutrients, keeping the whole system in a state of dynamic equilibrium. This BioOS 1.0 is running the planet's hardware, the geology, the oceans, the atmosphere. Now, the end Permian event is like a massive, multi-pronged cyber attack combined with a catastrophic hardware failure. The Siberian traps are like a colossal power surge that fries the main processors, global warming, and injects malicious code into the system, carbon acid rain. This initial attack targets fundamental parts of the operating system's environment. The rising heat and acid rain corrupt key files and processes, causing many applications, species, to crash immediately. This initial wave of crashes puts immense strain on the rest of the system. Suddenly, critical functions that were performed by these applications are no longer running. The code that governed moisture recycling by forests becomes corrupted and stops working. The subroutines that maintained oxygen levels in the ocean are overwhelmed by bad data, nutrient runoff and thermal stress, and they fail, leading to a system-wide anoxia error. The system starts to enter a cascade failure. The failure of one component puts more stress on others, causing them to fail as well. The positive feedback loops are like memory leaks or infinite loops in the code, consuming all the system's resources and driving it towards a total crash. The extinction is a kernel panic at a planetary scale. The entire operating system, BioOS 1.0, freezes and collapses. When the dust settles, the system has to reboot, but it can't reboot from the last saved version. That version is gone. It has to reboot from a deeply damaged state. Most of the code, most of the applications, have been permanently deleted. All that's left are a few very basic, very robust pieces of code, the safe mode organisms, our disaster taxa like Lystrosaurus. The reboot process is slow. The system has to be rebuilt, line by line, from this minimal, stripped-down version. The recovery is the long, slow process of writing a new operating system, BioOS 2.0. This new system will have a different architecture, different applications. The age of dinosaurs will be a key feature of this new OS. This analogy is, of course, imperfect. There is no programmer, no conscious design. The code of biology is written by the blind, undirected process of natural selection. But the analogy is useful because it helps us frame the extinction not just as a loss of species, but as a loss of information, a loss of complexity, and a failure of an entire system's architecture. It also helps us think about the nature of the recovery. Rebuilding a complex system takes far, far longer than destroying it. What does this operating system analogy imply about the nature of life and its resilience? It pushes us away from a view of biological systems as perfectly designed or optimized. An engineer designing an operating system from scratch might try to make it perfect, flawless, and efficient. But evolution doesn't work like that. It is a tinkerer, not an engineer. It works with what it has, modifying existing structures and code for new purposes. The result is not a system that is perfect, but one that is good enough to survive and reproduce in its current environment. BioOS 1.0 was not a perfect system. It had redundancies and resilience, but it also had latent vulnerabilities, hidden fragilities that were only exposed when the specific, multi-pronged stress of the end Permian event occurred. Its robustness was contingent, not absolute. This is a crucial distinction. It implies that survival is not about being the fittest in an abstract, absolute sense. Lystrosaurus was not better than a Gorgonopsian. In the stable world of the late Permian, the Gorgonopsian was a masterpiece of predatory evolution. But the definition of fitness is determined by the environment. When the environment changed catastrophically, the traits that defined fitness also changed. Suddenly, being a generalist, a burrower, or having a highly efficient respiratory system became more important than being a fast, powerful predator. The survivors were not the strongest or the most complex, but the most adaptable, or simply the most fortunate. This framework also emphasizes that systems can be designed for graceful failure. When a modern computer program crashes, it tries not to bring down the entire operating system. It fails in a contained way. The Permian extinction shows a system that did not fail gracefully. The collapse was total and catastrophic. The interconnectedness that gave the biosphere its richness and complexity also made it vulnerable to this kind of cascading failure. The tight coupling between the land and the sea, between the forests and the atmosphere, meant that a failure in one domain quickly spread to all the others. This gives us a new appreciation for the modularity and decoupling that can sometimes enhance resilience. Perhaps the biosphere that evolved after the extinction, BioOS 2.0, had a different architecture, with new firewalls and safeguards that made it more resilient to this specific type of global shock. The very act of surviving such an event is a powerful selective pressure that can shape the future of evolution for hundreds of millions of years. It's a planetary-scale lesson in systemic risk. So, our view of the Permian biosphere should not be one of a static, perfectly balanced idol that was tragically destroyed. It was a dynamic, messy, evolving system, full of intricate connections and hidden trade-offs. Its resilience was a product of its history, and its collapse was a product of a challenge that it had never before faced. The story is not about perfection versus destruction. It is about the limits of robustness in a complex, evolving system confronted by an unprecedented shock. It's a more complicated and perhaps more interesting story. To fully grasp the fragility of the Permian world, we must reconstruct its geography. Close your eyes for a moment and try to picture a map of the Earth. You see the familiar shapes of the continents, separated by vast oceans. Now, imagine taking those continents and pushing them all together, like pieces of a jigsaw puzzle, until they fuse into a single, colossal landmass. This is Pangea. This was the Earth at the end of the Permian period. Pangea stretched from the South Pole to the North Pole. It was shaped roughly like a giant sea, and the vast ocean that filled the curve of the sea is called the Tethys Sea. The rest of the planet was covered by a single, globe-spanning ocean called Panthalassa. This supercontinental configuration is not just a curious bit of trivia. It had profound and inescapable consequences for the planet's climate and the distribution of life. Let's build a sensory picture of this world. Stand in the center of Pangea. You are thousands of kilometers from the nearest ocean in any direction. The concept of a continental interior is taken to its absolute extreme. The climate here is brutally harsh. The moderating influence of the ocean is gone. The summers are scorchingly hot, and the winters are bitterly cold. It is also incredibly dry. Moisture from the ocean cannot penetrate this far inland. The weather is dominated by a giant mega-monsoon system. In the summer, the vast landmass heats up much faster than the ocean, creating a huge low-pressure system that draws in some moisture to the coastal regions. In the winter, the land cools down dramatically, creating a high-pressure system that pushes dry air outwards. The result is a climate of extremes, a brief, potentially violent wet season on the coasts, and a long, severe dry season, especially in the interior. The landscape in the heart of Pangea is a vast desert, larger than any that exists on Earth today. The rock record shows evidence of enormous dune fields and salt pans. Life here is sparse, clinging to the few oases and ephemeral rivers. Most of the biodiversity is concentrated in the more temperate and humid regions closer to the coasts of the Tethys Sea and in the high latitude zones to the north and south. The southern part of Pangea, known as Gondwana, is where the great glossopterid forests thrived in a more temperate, humid climate. The northern part, Laurasia, was dominated by conifers, but even in these more hospitable regions, the influence of the supercontinent was felt. There were fewer geographical barriers, like oceans or major mountain ranges, to stop the spread of species. This is why animals like Lystrosaurus could be found in what is now South Africa, India, and Antarctica. The terrestrial world was, in some ways, more homogeneous and interconnected than it is today. This unique geography is not just the stage on which the extinction drama played out. It was a key character in the story. We must now ask how this Pangean world, with its harsh climate and interconnected ecosystems, responded to the shock of the Siberian traps. Did the supercontinent itself create a world that was inherently more vulnerable to collapse? The geography of a supercontinent like Pangea creates a planetary system with a very specific set of characteristics and vulnerabilities. Let's analyze the consequences of this arrangement. First, the climate system. The lack of large oceans in the interior and the different ocean circulation patterns meant that the global climate was likely less stable and more prone to rapid shifts than our modern, fragmented continent world. The megamonsoon system is inherently a system of extremes. Small changes in the Earth's energy budget could have had a large effect on the strength and timing of this monsoon, leading to dramatic shifts between drought and flood. The planet's ability to buffer changes was reduced. There was less ocean surface area in the tropics to absorb heat, and the ocean circulation, which transports heat from the equator to the poles, was less efficient. This might have made the climate system more sensitive to a perturbation like the CO2 injection from the Siberian traps. A system that is already prone to extremes may have a lower tipping point. Second, the impact on the oceans. With one giant ocean, Panthalassa, circulation patterns were simpler and perhaps more sluggish. This could have made the ocean more susceptible to stratification, where the water column becomes layered and doesn't mix well. Poor mixing prevents oxygen from the surface from reaching the deep ocean, predisposing it to anoxia. When the climate warmed rapidly, this tendency towards sluggish circulation and stratification would have been massively amplified, helping to explain why the oceans lost their oxygen so quickly and so completely. The Tethys Sea, the semi-enclosed body of water, would have been particularly vulnerable to becoming stagnant and anoxic. Third, the consequences for biodiversity. The interconnectedness of life on Pangea might seem like a strength, but it could also have been a critical weakness. With fewer geographic barriers, there were fewer refugia, isolated areas where species could potentially survive a global crisis and then recolonize from. When the crisis hit, it hit everywhere at once. There was nowhere to hide. This lack of isolation may have led to a less genetically diverse and more homogeneous global ecosystem, making it more vulnerable to a single, overwhelming shock. In our modern world, a catastrophe in the Northern Hemisphere might spare ecosystems in Australia or Antarctica. On Pangea, the pathways for devastation to spread were wide open. Fourth, the supercontinent's role in the trigger itself. The very existence of Pangea may have played a role in creating the Siberian traps. The process of a supercontinent assembling and then sitting stagnant for tens of millions of years is thought to cause a build-up of heat in the mantle underneath it. The continent acts like a giant insulating blanket. This trapped heat can eventually lead to the formation of a massive mantle plume, a column of hot rock that rises and punches through the crust, creating a flood basalt province. In this view, the supercontinent created the conditions for its own near destruction. So, Pangea was not a passive backdrop. Its geography created a world with a sensitive climate, sluggish oceans, and interconnected, vulnerable ecosystems. It set the stage for a perfect storm. It created a system that was pre-wired for collapse. When the massive shock of the Siberian traps arrived, it hit a planetary system that was uniquely susceptible to the kind of cascading failure that ensued. The geography and the trigger were fatefully and fatally intertwined. Even in the face of such a compelling and multifaceted explanation, a healthy scientific mindset requires us to actively seek out criticism and potential falsifiers. What are the strongest arguments against the mainstream synthesis we have built? Where are its weakest points? Let's step into the shoes of a skeptic and rigorously test the model. A major point of contention for some researchers is the kill mechanism on land. While the model of heat stress, drought, and ecosystem collapse is powerful, some argue it is not sufficient to explain the sheer speed and severity of the terrestrial extinction. They ask, could animals not have migrated to the cooler polar regions? Could burrowing animals not have survived the heat? These critics often look for a more direct, acute poison. One proposal, which we touched on, is the release of hydrogen sulfide from the anoxic oceans. In this scenario, the gas would bubble into the atmosphere, directly poisoning terrestrial life and, by damaging the ozone layer, exposing it to lethal UV radiation. Evidence for this is suggestive but not conclusive. Some studies have found malformed fossil spores and pollen from the PT boundary, which could be interpreted as evidence of UV damage. However, directly proving that H2S reached lethally toxic levels in the atmosphere is extremely difficult. The mainstream model can be criticized for not fully accounting for this potential kill mechanism. Another area of skepticism relates to the timing and tempo. While the overall synchrony between the volcanism and the extinction is clear, the fine details are messy. Some high-resolution geological records seem to show that significant ecosystem stress and some extinctions were already underway before the main pulse of volcanism and the giant carbon isotope excursion. If this is true, it complicates the simple trigger and response narrative. It might imply that the Earth system was already destabilized for some other reason, and the Siberian traps were just the final, fatal blow. What could this prior stress be? Some have pointed to other, smaller volcanic episodes or earlier shifts in climate. This doesn't disprove the central role of the Siberian traps, but it suggests the story might be one of a 1-2 punch rather than a single knockout blow. The model could be falsified, or at least significantly revised, if several things were discovered. If a large, unambiguously dated impact crater was found, right at the PT boundary, along with a clear global iridium layer, the impact hypothesis would have to be given a much more central role. The entire model would need to be re-evaluated to see if the two events could be linked, or if one was more important than the other. Another potential falsifier would be the discovery of a high-latitude or deep ocean ecosystem that sailed through the extinction event completely unscathed. If a complex reef system, for example, was found to have survived without any major loss of diversity, it would challenge our understanding of the extinction as a truly global event with global kill mechanisms like anoxia and acidification. So far, no such magic refuge has been found. The extinction appears to have been truly democratic in its devastation. Finally, if a new, more detailed analysis of the Siberian traps showed that the vast majority of the gas release happened after the extinction was already complete, it would sever the causal link that is the foundation of the entire theory. This seems highly unlikely given the current high-quality dating evidence, but it remains a theoretical possibility. A good scientific theory is not one that is proven true, but one that is rigorously tested and survives all attempts to falsify it. The Siberian trap synthesis has, so far, survived these tests better than any of its rivals. But the criticisms and the search for falsifying evidence are what drive the science forward, forcing us to refine our models and seek out new data to fill in the gaps in our understanding. Our role in this investigation is like that of a detective trying to solve a cold case based on a series of faded, partially destroyed photographs taken by different cameras, at different times, from different angles. This is the meta-method of deep time geology. We are dealing with layers of incomplete information, and our own cognitive biases can shape how we assemble the puzzle. Let's think about the mindset required. A key concept is the use of priors. When we approach the data, we are not a blank slate. We have a pre-existing understanding of how physics, chemistry, and biology work. This is our prior model of the world. When we see a massive, negative carbon isotope excursion, our prior knowledge of the carbon cycle immediately tells us to look for a massive source of light carbon. This is a powerful tool, but it can also be a trap. If our prior model is wrong or incomplete, it can lead us to misinterpret the data. This is why it's so important to be willing to question our own assumptions, to ask if there's another way to interpret the signal. Anomalies are the most important things in this kind of science. When a piece of data doesn't fit the prevailing model, it's tempting to dismiss it as an error or an outlier. But the detective mindset requires us to cherish anomalies. An anomaly is a loose thread. If you pull on it, it might just be a stray piece of lint, or it might unravel the entire fabric of your current theory. The debate over whether the extinction started before the main volcanic pulse is a perfect example. It's an anomaly that forces us to question the simplest version of the story and consider a more complex multi-stage process. We also have to be acutely aware of erasure. The geological record is a story of erasure. Tectonic plates are subducted, carrying their history down into the mantle forever. Mountains are eroded to dust. The ocean floor is almost entirely recycled every 200 million years. This means we have virtually no deep ocean crust left from the Permian. Our entire record of the Panthalassic Ocean comes from scraps of crust that were scraped off and preserved on the edges of continents. We are trying to understand a global ocean from a few tiny windows. We must constantly ask ourselves, what are we not seeing? What evidence has been permanently destroyed? Our picture of the world is necessarily biased towards the continental and shallow marine environments that are most likely to be preserved. This detective mindset means we are always operating in a state of provisional truth. We build the most coherent narrative we can from the available clues, the one that explains the most evidence with the fewest contradictions. This is the principle of Occam's razor. The Siberian traps hypothesis is so powerful because it is so parsimonious. It links together a huge range of disparate observations with a single, overarching causal chain. But we must never mistake our current best explanation for the final truth. We must always be looking for the next clue, the next anomaly, the next piece of evidence that will force us to reconsider. This is the discipline and the humility required to read the book of the Earth. The story is not finished. We are still in the middle of deciphering it. Let's now bring this abstract thinking back to the human scale to reground ourselves before we proceed. Let's pull back from the immense scale of geological time and planetary systems and return for a moment to this room, to your body. Feel, once again, the physical reality of your presence here, the gentle rise and fall of your chest, the contact between your body and the surface supporting you, the ambient temperature of the air. We've been on a long and complex journey, and it's easy to feel disconnected from the tangible world when immersed in such deep abstractions. But the story of the Permian is not just an abstract scientific model. It is a story about the material world. It is a story about the same carbon, oxygen, and water atoms that are currently circulating through your own body. The carbon atom you just exhaled in a breath of CO2 may have once been part of a glossopterid leaf, released into the atmosphere during the Great Permian die-off, cycled through the ocean for millions of years, and is now, briefly, a part of you. You are, in a very real and physical sense, a continuation of this story. You are made of the planet's history. This recognition can shift our perspective. The deep past is not something entirely separate from us. It is the foundation on which our present moment is built. The oxygen-rich atmosphere we depend on, the stable climate we have inherited, the very soil that grows our food, these are all legacies of the planet's turbulent history and its long, slow recovery from past catastrophes. Recognizing this connection doesn't require us to do anything in particular. It's not a call to action, but a call to awareness. It's an invitation to feel yourself as a participant in this vast, ancient, and ongoing planetary system. The simple, autonomous act of breathing is your body's participation in the carbon and oxygen cycles. The water you drink is your participation in the hydrologic cycle. You are not separate from these systems. You are these systems, manifest in a temporary, localized form. This embodied understanding can give us a different kind of agency. It is not the agency of control or domination, but the agency of attention and care. By understanding the fragility that this planetary story reveals, we can bring a greater sense of mindfulness to our own interactions with the world around us. We can begin to see the grand, abstract cycles of the Earth reflected in the small, concrete details of our daily lives. The story of the Permian is a stark reminder that the world's life support systems are a precious and contingent inheritance. Grounding ourselves in this physical, present moment, feeling our own aliveness, is perhaps the most fitting way to honor the memory of the world that was lost, and to appreciate the resilience that allowed life to continue, and eventually for us to be here now, contemplating it all. Let's now introduce another lens for looking at the Earth system, the flow of energy. A planet's climate is fundamentally governed by its energy budget. The Earth receives a certain amount of energy from the Sun in the form of shortwave radiation, light. To maintain a stable temperature, it must radiate the same amount of energy back out into space in the form of long-wave radiation, heat. If the energy coming in is greater than the energy going out, the planet warms up. If the energy going out is greater than the energy coming in, it cools down. Greenhouse gases, like carbon dioxide, don't stop the incoming energy from the sun, but they do make it harder for the outgoing heat radiation to escape. They act like a blanket, trapping heat in the lower atmosphere. So, when we add a massive amount of CO2 to the atmosphere, as happened at the end of the Permian, we are fundamentally altering the planet's energy budget. We are reducing the efficiency with which the planet can cool itself. This creates an energy imbalance. More energy is coming in than is going out. This excess energy is what drives global warming. It heats the atmosphere, it heats the land, and the vast majority of it, over 90%, is absorbed by the oceans. This is a crucial point. The oceans are the planet's great heat sink. The temperature of the atmosphere is just the tip of the iceberg. The real measure of the planet's warming is the heat content of its oceans. Let's put some rough numbers to the Permian event based on climate models. The forcing from the greenhouse gas release was likely on the order of 10 to 15 watts per square metre of the Earth's surface. For comparison, the forcing from all human-caused greenhouse gases since the Industrial Revolution is about 3 watts per square metre. So the initial energetic shock of the Permian event was perhaps 3 to 5 times larger than our current one. This massive energy imbalance is what drove the whole cascade. The warming of the ocean surface is a direct consequence of the ocean absorbing this excess energy. The stratification of the ocean is also an energy story. A warm, buoyant layer of water on top cannot easily mix with the cold, dense water below. The system becomes physically stable in a way that is biologically disastrous. The increased intensity of storms is also a story about energy. Storms are heat engines that take the energy from warm ocean water and convert it into the kinetic energy of wind. A hotter planet with warmer oceans is a planet with more fuel for more powerful storms. The erosion we see in the rock record is a consequence of this increased energy in the climate system. What this energy budget perspective shows us is that the Permian extinction was, at its core, a thermodynamic crisis. The massive release of carbon fundamentally broke the planet's ability to regulate its own temperature. The system was thrown into a state of severe energy imbalance, and all the biological consequences, the extinctions, the anoxia, the ecosystem collapse, were downstream effects of the planet's physical systems struggling to cope with this enormous influx of trapped heat. This lens allows us to quantify the scale of the insult to the planetary system. It moves beyond qualitative descriptions of hot and cold to the underlying physics of energy flows. It shows that the rules of thermodynamics are the ultimate arbiters of a planet's fate. The intricate systems of biology can only function within a certain thermodynamic window. The Permian extinction was what happened when the planet was violently pushed out of that window. The energy budget perspective allows us to explore the sensitivity of the system and consider the second-order trade-offs and consequences. Once we understand that the core problem was a massive energy imbalance, we can ask more nuanced questions about how that energy was distributed and what its knock-on effects were. For example, we've established that the poles would have warmed much more than the equator. This polar amplification is a standard feature of greenhouse warming. What are the implications of this? A reduced temperature gradient between the equator and the poles would weaken the jet stream and the large-scale atmospheric circulation patterns that drive weather. This could lead to more persistent and extreme weather events, longer droughts, more intense heat waves, and more stalled weather systems. The climate would become not just hotter, but more erratic and less predictable. The energy influx also has direct consequences for life beyond just the temperature. Higher temperatures increase the metabolic rates of organisms. In the oceans, this means marine animals need more oxygen to fuel their higher metabolism, at the very same time that the warming water contains less available oxygen. This creates a metabolic crunch, or a squeeze, where the oxygen demand of organisms outstrips the environmental supply. This mechanism alone can explain why many species, particularly large active predators, went extinct. They were caught in a physiological vice. We can also consider the trade-offs. The massive volcanic eruptions released both warming gases, like CO2, and cooling aerosols, like sulfates. For the first few years after a major eruptive pulse, the cooling effect of the aerosols might dominate, creating a brief but intense volcanic winter. But the aerosols rain out of the atmosphere in a matter of years, while the CO2 remains for centuries to millennia. So the system would have experienced a series of sharp cooling shocks, followed by a relentless, long-term warming trend. This whiplash effect would have been incredibly stressful for ecosystems, which were being hit by contradictory climate signals in rapid succession. There are multiple plausible mechanisms at play, and it's not always an either-or situation. Was the marine extinction caused by heat, anoxia, or acidification? The answer is likely all of the above. These stressors were acting in concert, and their combined effect was likely greater than the sum of their parts. This is a key feature of complex system collapse. The failures are synergistic. The energy budget framework helps us see how the single primary shock, the trapping of heat, could manifest as a whole suite of different but interconnected environmental stresses. It highlights the sensitivity of the entire Earth system to its energy balance. A small change in the efficiency of outgoing radiation, sustained over a long enough time, can lead to a complete reorganization of the climate and a catastrophic failure of the biosphere. It underscores that the stability of our world depends on a very precise and delicate thermodynamic equilibrium. Is it possible that the memory of such profound collapses, of worlds ending and beginning anew, is encoded not just in rocks, but also in human stories? This is a delicate and speculative area of inquiry, but one worth touching upon with care. Let's be clear, we are not suggesting that ancient myths contain literal, scientific accounts of the Permian extinction. The event happened more than 250 million years before the first humans evolved. There can be no direct cultural memory of it. However, humanity's much more recent history has been filled with its own catastrophic events. Supervolcanic eruptions, mega floods from melting ice age glaciers, tsunamis and abrupt climate shifts. It is possible that our oldest narratives, our creation myths, our flood stories, our tales of world-ending cataclysms, are cultural echoes of these more recent human timescale traumas. Many cultures around the world have a great flood story. The story of Noah in the Judeo-Christian tradition, the Epic of Gilgamesh in Mesopotamia, the Manu story in Hindu mythology, and countless others. For a long time, these were dismissed as mere fables. But geologists have discovered that at the end of the last ice age, around 7,500 years ago, the rising Mediterranean Sea catastrophically broke through the Bosporus sill and flooded the Black Sea basin, which at the time was a freshwater lake. This would have been a terrifying, world-altering event for the people living on its shores. The water would have advanced at a relentless pace, wiping out settlements and transforming the landscape. It's plausible that this event, or others like it in different parts of the world, became the seed of the great flood myths. Similarly, many mythologies contain stories of a world consumed by fire, or a sun that burns too hot, or a long period of darkness. The Ragnarok of Norse mythology describes a world consumed by fire and flood before being born anew. These stories could be distant, mythologized memories of major volcanic eruptions that darkened the sky for years, or of severe multi-year droughts that felt like the sun itself had turned against humanity. What is the connection to the Permian? The connection is not in the details, but in the archetypal pattern. These stories reveal a deep-seated human understanding that the world is not stable, that order can collapse into chaos, and that life is a fragile thing built upon a powerful and sometimes violent earth. They are stories about crossing thresholds. They encode a kind of pre-scientific, intuitive systems thinking. The myths often describe a world that has fallen out of balance due to some transgression, leading to a divine or natural retribution that purges the old world to make way for a new one. This narrative structure, stability, transgression, collapse, and renewal, mirrors the deep time pattern of mass extinctions that we see in the geological record. This is not to say the patterns are identical, or that one explains the other, but it suggests that human storytelling and scientific modeling may be two different languages trying to describe the same fundamental truths about living on a dynamic and powerful planet. The myths capture the emotional and psychological reality of catastrophic change, while the science captures the physical and chemical mechanisms. By holding them side by side, we can appreciate the continuity of the human struggle to make sense of a world that is much older, larger, and more powerful than we are. So far, we have assembled the key components of the story. We have a trigger in the form of the Siberian traps. We have a primary mechanism in the massive release of greenhouse gases. We have a cascade of environmental consequences, global warming, ocean anoxia, acidification, and we have a unique geographical context in the supercontinent of Pangea. We have seen how these pieces fit together, but now we must perform a crucial intellectual turn. We must move away from a simple, linear chain of cause and effect and begin to see this event as a fully interconnected, non-linear system failure. We will soon synthesize these threads into a more holistic model, one that emphasizes the feedback loops and synergistic stresses that made this event the Great Dying. The key will be to stop thinking in terms of this caused that, and start thinking in terms of a system's properties changing all at once in a self-reinforcing death spiral. This reframing is the next step in deepening our understanding. The intellectual turn we need to make is to move from a linear, binary way of thinking to a more continuous and systemic one. It's easy to frame the question as an either-or debate. Was it volcanoes or an impact? Was it CO2 or methane? Was the cause geological or biological? But the deeper we look, the more these binaries dissolve. The evidence does not point to a single, neat cause, but to a convergence of multiple factors, a perfect storm where the whole was far more destructive than the sum of its parts. Let's replace the binary of volcanoes versus impact with a continuum of planetary stress. The Earth system is always being subjected to various stresses, both internal, like volcanism, and external, like impacts. The Permian extinction was likely a case where a massive internal stress, the Siberian traps, pushed the system to a tipping point, making it incredibly vulnerable. In this state, other smaller stresses that the system could normally handle, perhaps a smaller impact or a natural fluctuation in methane release, could have had a disproportionately large effect. The question is not which one was the cause, but how they interacted. Instead of CO2 or methane, let's think of a spectrum of greenhouse forcing and feedback. The initial injection of CO2 from the volcanoes and cooked coal beds was the primary driver. This was the initial push. But this initial warming then triggered secondary releases of other greenhouse gases, like methane from clathrates and more CO2 from dying forests. It wasn't one or the other, it was a sequence. The CO2 was the long-burning fuse, and the methane was the explosive charge it ignited. They work together in a powerful positive feedback loop. The binary of geological versus biological cause also dissolves. The trigger was geological, the volcanism, but the catastrophe was amplified and sustained by the biological response. The collapse of the forests turned a carbon sink into a source. The bloom of methane-producing microbes in the ocean may have been a key accelerator. The death of the biosphere fed back to make the physical environment even more hostile. The geology and the biology were locked in a fatal embrace. This systemic view changes how we understand causality itself. In a complex interconnected system, causality is not a straight line. It's a web. The Siberian traps are not the cause of the extinction in the way a single billiard ball causes another to move. They are the initiating perturbation in a system that was predisposed to catastrophic failure, and which then entered a runaway state of self-amplifying collapse. This reframing has implications for how we think about risk and resilience in our own time. It suggests that we should be less focused on identifying a single specific threat and more focused on understanding the overall resilience and hidden vulnerabilities of our own planetary systems. The danger is not just the initial shock, but the potential for that shock to trigger unforeseen, cascading failures. The Permian story teaches us that when a planetary system is pushed hard enough, the distinctions we make between atmosphere, ocean, rock, and life become meaningless. It all becomes one system, failing together. This is the crucial turn in our understanding, from a collection of parts to a single, integrated, and collapsing whole. Let's now try to synthesize these various evidence tracks into a single coherent model. We will connect the microscale mechanisms to the macroscale patterns, building the story of the collapse step by step, not as a simple line, but as a web of interactions. Our starting point is the late Permian world, a world with a Pangean geography. This geography, as we've seen, creates a system with inherent sensitivities, a sluggish ocean circulation, and a climate prone to extremes. This is our baseline state, the pre-existing condition. Into this world, we introduce the initiating perturbation, the emplacement of the Siberian trap's large igneous province. This is not a single event, but a process lasting hundreds of thousands of years, with intense pulses. Phase 1. The opening act. The first volcanic pulses release massive quantities of sulfur aerosols into the stratosphere. This leads to a brief but significant global cooling, volcanic winter, and widespread, intense acid rain. This initial shock does not cause the mass extinction, but it severely stresses terrestrial and marine ecosystems. The forests are weakened, and the chemistry of the surface ocean begins to change. The system's resilience is lowered. Phase 2, the main event, the carbon injection. The main eruptive phase begins. Magma intrudes into the vast Siberian coal and gas basin, cooking the organic-rich sediments and releasing staggering amounts of isotopically light carbon, as CO2 and methane, directly into the atmosphere. This is the event recorded by the sharp negative carbon isotope excursion worldwide. This is the primary forcing that initiates the runaway greenhouse effect. Phase 3. The atmospheric and terrestrial response. The massive influx of greenhouse gases overwhelms the planet's carbon sinks. Atmospheric CO2 levels skyrocket, perhaps to several thousand parts per million. The global energy budget is thrown into severe imbalance, leading to a rapid and intense global warming of 5 to 10 degrees Celsius or more. On land, the combination of this extreme heat, persistent drought in the continental interior, and the lingering effects of acid rain leads to a catastrophic dieback of the forests. This terrestrial ecosystem collapse has two immediate feedback effects. It turns the massive carbon sink of the biosphere into a carbon source, amplifying the warming, and it leads to massive soil erosion, washing nutrients and sediment into the oceans. Phase 4. The oceanic cascade. The oceans are now being assaulted from above and from the sides. From above, the warming atmosphere heats the ocean surface, reducing oxygen solubility and increasing stratification. The high atmospheric CO2 dissolves into the water, causing rapid ocean acidification. From the sides, the rivers, choked with sediment and nutrients from the dying land, pour into the coastal zones, fueling massive algal blooms. When these blooms die and sink, their decomposition consumes the remaining oxygen, creating widespread anoxia. Phase 5. The amplifying feedbacks. The system is now in a death spiral, driven by positive feedbacks. The warming of the deep oceans may cross a threshold, destabilizing methane clathrates and releasing yet more potent greenhouse gas, further amplifying the warming. As anoxia spreads, the oceans become a breeding ground for sulfate-reducing bacteria, which produce toxic hydrogen sulfide. This H2S poisons the oceans and may have been vented into the atmosphere, creating another direct killing mechanism on land and damaging the ozone layer. Phase 6. The extinction pulse. At the confluence of all these stresses, extreme heat, lack of oxygen, acidic and poisoned waters, potential UV radiation exposure, the biosphere collapses. The extinction is not caused by any one of these factors, but by their synergistic combination. Organisms are faced with multiple simultaneous crises that exceed their physiological tolerances. The result is the loss of up to 96% of marine species and 70% of terrestrial vertebrate species in a geologically short period. This synthesized model connects all our evidence tracks. It links the macro-scale geology of Pangea and the Siberian traps, Track 7 and the mainstream objection, to the micro-scale chemical evidence of isotopes and biomarkers, Track 4. It shows how the collapse of the biome-atmosphere conversation, Track 5, acts as a crucial feedback. It provides a physical basis for the patterns we see in the fossil record, Track 1. And it frames the entire event as a catastrophic failure of the planet's regulatory systems and feedback loops, Track 2. It is a story of a system pushed beyond its breaking point, where every component of the planetary machinery begins to contribute to the escalating failure. Even with this comprehensive synthesis, we must explicitly acknowledge what remains unknown and where the major points of scientific debate still lie. A complete picture requires us to map the boundaries of our knowledge and the terrain of our uncertainty. One of the biggest areas of uncertainty remains the precise tempo and timing of the collapse. We know the whole event was geologically rapid, but was the main extinction pulse a single, sharp catastrophe that took place over just a few thousand years? Or was it a series of closely spaced pulses of extinction spread out over 60,000 years? The resolution of the rock record is often not fine enough to definitively distinguish between these scenarios. Answering this question is critical, as a very fast single pulse might point more towards a catastrophic trigger, like an atmospheric H2S burp, while a more stepwise collapse might better fit a model driven by the pulsing nature of the volcanism. Another major unknown is the specific hierarchy of kill mechanisms. We have a list of suspects: heat stress, anoxia, acidification, hydrogen sulfide poisoning, and perhaps others like metal poisoning from volcanic fallout. But what was the relative importance of each? Was anoxia the primary killer in the oceans, or was it acidification? Did most terrestrial animals die from heat, or were they poisoned? The answer likely varied by region and by type of organism. Untangling this complex web of lethality is a major focus of current research, often involving studying the physiology of modern organisms to see how they respond to Permian-like stress conditions. We also don't fully understand the recovery. Why did it take so long? Up to 5 million years. For complex ecosystems like reefs and forests to re-establish themselves. The immediate aftermath was dominated by disaster taxa, but the subsequent period, the early Triassic, was a strange, unstable world with wild climate swings. This suggests that the extinction didn't just wipe out the species, it fundamentally broke the planet's stabilizing feedback mechanisms. The planetary thermostat was not just turned up, it was damaged, and it took millions of years to repair. The exact processes that governed this slow, painful recovery are still poorly understood. The next steps in research will involve a multi-pronged approach. Scientists are constantly searching for new, more complete geological sections across the PT boundary, especially in underexplored regions. They are developing new geochemical proxies that might allow us to, for instance, directly measure the pH of the ancient ocean or track the levels of H2S. Higher resolution dating techniques are constantly pushing the boundaries of how precisely we can correlate events around the globe. And increasingly sophisticated computer models are being used to simulate the Permian climate system, allowing scientists to test different hypotheses and see which scenarios best match the geological data. The key is to recognize that our current synthesis is not an endpoint. It is a working model, the best one we have given the current evidence. It is a remarkably successful model that explains a huge range of observations. But science is a process of refinement. The questions that remain are the exciting frontiers of the discipline. They are the puzzles that ensure that the story of the Great Dying is not just a settled piece of history, but a vibrant and active field of scientific discovery. Let's walk through this synthesized model one last time, but from a second-person perspective. Let's place you on the shores of the Tethys Sea at the very end of the Permian and let you experience the unraveling of the world. You are standing on a beach. The sand is dark, volcanic. Behind you, a forest of glossopterid trees stands, their leaves looking unusually sparse and sickly. For the past few years, the rain has been acidic and strange, and the world has felt off balance. The sky is often hazy, filled with a persistent volcanic smog from the eruptions half a world away. You look out at the ocean. It should be a vibrant turquoise, teeming with life. But the water has a strange, stagnant quality. There are no fish breaking the surface. The reefs close to shore, which used to be bustling cities of brachiopods and strange sponges, are now ghostly white and crumbling. The water is becoming more acidic, dissolving the very foundations of marine life. You wade into the water. It is unnervingly warm, like a bath. This warmth is pleasant for a moment, but it is a symptom of a planetary fever. This heat is what is suffocating the ocean, preventing oxygen from the surface from mixing into the depths. A foul, sulphurous smell, the faint scent of rotten eggs, wafts in on the breeze. It's the smell of the deep ocean's decay, the hydrogen sulfide produced in the anoxic depths that is beginning to well up to the surface. It is the smell of death. Weeks pass. The heat becomes relentless. The sun beats down from a hazy greenhouse sky. The forest behind you is dying. Trees are collapsing, their wood providing fuel for vast, spontaneous wildfires that paint the horizon with a smoky orange glow. The animals of the forest are gone. There is an eerie silence broken only by the wind. You look at the ocean again, and you see a horrifying sight. A slick of purple and pink bacteria has appeared on the surface. These are the microbes that thrive in anoxic, sulfide-rich water. The ocean is visibly toxic. The normal cycle of life has been replaced by a strange, alien metabolism. At night, the water sometimes has a faint, chemiluminescent glow, a ghost light from a dying sea. Your own body is struggling. The air is thin, low in oxygen. Every breath is an effort. The high CO2 levels may be affecting your own blood chemistry. The world around you, the world that has sustained your ancestors for millions of years, has become an alien planet. It is actively trying to kill you. You see now that everything is connected. The haze in the sky is linked to the heat you feel on your skin. The heat is linked to the warmth of the water. The warmth of the water is linked to the lack of oxygen. The lack of oxygen is linked to the poison that is being produced in the depths. The death of the forest on land is feeding the death in the sea. It is not one thing that is wrong. It is everything, all at once. The system that supports life is now the system that is extinguishing it. You are a witness to the moment when a planet's life support system fails. You are standing at the end of a world. This entire exploration of a distant, catastrophic past can feel overwhelming, abstract, and perhaps even disempowering. But what if we could translate some of the insights from this deep time story into small, testable practices for our own attention and agency, right here and now? This is not about prescribing solutions to modern problems or drawing simplistic one-to-one analogies. It is about using the Permian story as a lens to see our own world and our place in it with new eyes. First, we can practice seeing the systems around us. The Permian story is a lesson in interconnectedness. We can practice this way of seeing in our own lives. The next time you drink a glass of water, take a moment to consider the vast hydrologic cycle you are participating in. The water in your glass has a history that stretches back eons. The next time you eat a piece of fruit, consider the biological and geological systems that brought it to you. The soil, the sun, the pollinating insects, the carbon cycle that built the plant's tissues. This is not an intellectual exercise. It's a practice of attention. It is about shifting from seeing a world of separate objects to seeing a world of nested, interacting systems. Second, we can practice noticing feedback loops. The Permian collapse was driven by runaway positive feedbacks. We can learn to spot these in our own lives and environments, both positive and negative. Notice how a simple act of kindness can create a positive social feedback loop. Notice how a moment of anxiety can sometimes trigger a spiral of more anxious thoughts, a negative mental feedback loop. On a larger scale, we can see how planting trees in a neighborhood can create a positive feedback of cooling, cleaner air, and greater well-being. By learning to recognize the structure of feedback, we become more attuned to the dynamics of the systems we are part of. This is a form of systems literacy. Third, we can cultivate a deeper sense of time. Our modern world often operates on a timescale of seconds, days, or quarterly reports. The Permian story invites us to zoom out. We can practice this by paying attention to the slower rhythms around us. Notice the cycle of the seasons. Visit a place with exposed rock and try to imagine the immense history contained within it. Contemplate the lifespan of a tree. This practice of deep time awareness can help to place our own immediate concerns in a broader, more expansive context. It can foster patience and a longer-term perspective. These are not grand, world-changing actions. They are small, local-first practices of attention. They do not require any particular belief or ideology. They simply require a willingness to look at the world with the kind of curiosity and systemic awareness that our journey to the Permian has hopefully inspired. They are a way of taking the intellectual model we have built and translating it into a lived, embodied experience. It is a way of recognizing that we are not just observers of the Earth system. We are it. Where does the Earth system go from here? Looking at the deep past invites us to think about the deep future. This is not about making concrete predictions, which is impossible, but about exploring plausible scenarios based on our understanding of how the planet works. We must be very clear about our confidence levels here. This is bounded speculation. One plausible long-term future, on the scale of tens to hundreds of millions of years, is governed by the slow, predictable dance of plate tectonics. The continents are still moving. The Atlantic Ocean is currently widening, and the Pacific is shrinking. Projections suggest that in about 250 million years, the continents may once again merge to form a new supercontinent. The shape and location of this Pangea Ultima are debated, but the process of supercontinent formation seems to be a recurring cycle in Earth's history. This future world would have its own unique climate, with vast interior deserts and mega monsoons, just as the original Pangea did. It would be another chapter in the planet's long story of geographic transformation. On a shorter, but still geological timescale of millions of years, the Earth's climate will continue to be governed by orbital cycles, the Milankovitch cycles, and the long-term carbon cycle. The planet will likely continue to oscillate between ice ages and warmer interglacial periods, driven by subtle changes in the Earth's orbit, as long as there is some ice at the poles. The slow process of silicate weathering, where rocks draw down CO2 from the atmosphere, will continue to act as the planet's long-term thermostat, operating on a timescale of hundreds of thousands of years. The open questions about the future are mostly about the role of life. The Permian extinction shows that the biosphere can be a powerful actor, both in its collapse and its recovery. What new evolutionary innovations will emerge over the next few million years? What new kinds of ecosystems will form? The history of life is a story of constant, surprising creativity. The extinction of the dinosaurs cleared the way for the age of mammals. The Permian extinction cleared the way for the age of dinosaurs. Each mass extinction has, in the long run, been followed by a burst of evolutionary novelty. It is plausible to assume this fundamental pattern will continue. The most profound open question, of course, concerns our own role in the planet's future. We are now a geological force in our own right, altering the carbon cycle, the nitrogen cycle, and the biosphere at a rate that is, for some parameters, faster than what we saw at the end of the Permian. The long-term consequences of this Anthropocene perturbation are unknown. Will the Earth system's negative feedbacks be strong enough to absorb this shock and return to a state similar to the one we inherited? Or have we pushed the system across a threshold towards a new, hotter, and potentially less hospitable hothouse Earth state that could last for millennia? The rocks of the Permian do not give us an answer to this question. They only give us a warning. They show us what is possible. They show us the planetary-scale consequences of a massive, rapid perturbation to the carbon cycle. The future is not written in stone, but the past is. And its lessons are there for us to read if we have the wisdom to do so. After such a long and detailed journey through the mechanics of planetary collapse, it's important to pause and reframe this intellectual model into something more felt, more meaningful. What does it feel like to carry this story? For one, it can cultivate a profound sense of awe. To contemplate a world so ancient and so alien, to trace the evidence of its existence in the faintest chemical whispers in a piece of rock, is to be confronted with the sheer scale and grandeur of time. It is to recognize that our own lives, and even the entire history of our species, are but a brief flash in an immense and ongoing cosmic drama. This is not a diminishing feeling, but an expanding one. It connects us to a story that is vastly larger than ourselves. The story also evokes a deep sense of sobriety and humility. The Permian extinction is a stark reminder of the planet's power and our own fragility. It shows that the conditions for life, even for a biosphere as mature and complex as the Permian one, are not guaranteed. The Earth does not have a vested interest in our survival, or the survival of any particular species. It operates according to the laws of chemistry and physics. The stability we enjoy is a contingent gift of the planet's current equilibrium, not a permanent right. This humility is not despair. It is a clear-eyed recognition of reality, but perhaps the most surprising emotional reframe is a deeper appreciation for the resilience of life itself. Yes, the Permian extinction was a story of almost unimaginable death, but it is also necessarily a story of survival. Life was pushed to the absolute brink. The planet was transformed into a toxic furnace, and yet life endured. A few hardy species in a few scattered refugia held on, and from those survivors the entire magnificent diversity of the modern world was eventually born. Every bird, every mammal, every lizard, every flower, all are descendants of the species that made it through the crucible of the great dying. This is a staggering thought. It means that the lineage of life to which we belong is defined by an almost unbelievable tenacity. It has survived planetary freezes, asteroid impacts, and the hellscape of the end Permian. This does not make life invincible, far from it, but it does speak to a deep, persistent, creative force that is woven into the fabric of this planet. So, the story of the Permian extinction, in the end, is not just a story about death. It is a story about the relationship between destruction and creation. It is a story about the terrifying fragility and the astonishing resilience of the living world. To hold both of these truths in mind at the same time, the fragility and the resilience, is to arrive at a more complete and ultimately more hopeful understanding of our place on this beautiful and dangerous planet. Where does our scientific model end, and where does the human search for meaning begin? This is the philosophical boundary of our inquiry. The scientific method is an incredibly powerful tool for answering what and how questions. What happened at the end of the Permian? How did the Earth system fail? We can build robust, evidence-based models to answer these, but science is not designed to answer why questions, at least not in the sense of purpose or meaning. Why did this happen? Is there a purpose to these cycles of creation and destruction? Was the Permian extinction a tragedy, or was it a necessary clearing of the slate for new forms of life to emerge? These are not scientific questions. The data cannot answer them. The rocks are silent on the matter of meaning. This is where we must be intellectually honest and recognize the limits of our tools. The geological record can tell us that 96% of marine species went extinct. It cannot tell us whether this was bad. That is a value judgment we bring to the story. The model can tell us that the survivors gave rise to the dinosaurs and eventually to us. It cannot tell us whether this was good. That is a narrative we impose upon the facts. This boundary is not a failing of science. It is a necessary and important distinction. Science provides us with the most reliable description of the physical world. It gives us the raw material for our philosophies, our ethics, and our stories. But it does not provide the meaning itself. The search for meaning is a fundamentally human act. We are the ones who look at the data of the great dying and feel awe or terror or humility. We are the ones who see in it a cautionary tale, or a story of resilience, or a testament to the indifference of the cosmos. The choice of which story to tell, which meaning to make, is ours. We can choose to see the Permian extinction as a story of pure, random catastrophe, a demonstration that the universe is chaotic and meaningless. Or we can choose to see it as part of a larger, cyclical pattern, a deep rhythm of death and rebirth that is inherent to the nature of this planet. Both are valid interpretations of the same set of facts. Science can constrain our stories. Any meaning we make must be consistent with the evidence, but it cannot choose our stories for us. So we hold the question open. We sit with the profound ambiguity of it all. We can marvel at the intricate causal chain that led to the collapse, while at the same time acknowledging that the ultimate why remains a mystery. This is a space for wonder, for contemplation, and for a kind of intellectual humility that recognizes that not all questions can be answered by data. The story of the Permian takes us to the very edge of what we can know and invites us to look out into the vast, silent ocean of what we can only imagine. When confronted with a system as complex and seemingly fine-tuned for life as our planet, it's natural for two different frames of mind to emerge. One is a frame of emergence, and the other is a frame that leans towards anthropic or design-oriented thinking. Let's compare these two frames not as a debate to be won, but as two parallel ways of contemplating the same reality, both rooted in a sense of humility. The emergence frame is the native language of complexity science, and the one we have primarily used in our exploration. In this view, the properties of the Earth system that support life, its stable climate, its oxygen-rich atmosphere, its self-regulating cycles, are not designed or intended. They are emergent properties. They arise spontaneously from the interactions of countless individual components, governed by the basic laws of physics and chemistry. The planet is not trying to be habitable. It just so happens that the particular set of feedback loops that developed on this planet over billions of years resulted in a system that is conducive to complex life. Stability is a contingent outcome of the system's history, not its purpose. From this perspective, a mass extinction is a natural, albeit extreme, part of the system's behavior. It is a phase transition, a moment when the system is pushed into a different state. There is no malice or intent, only cause and effect rippling through a complex network. The awe in this viewpoint comes from the recognition that such profound order and complexity can arise from such simple underlying rules, without a blueprint. The second frame, the anthropic or design frame, looks at the same evidence and asks a different kind of question. It observes the sheer unlikeliness of it all. The Earth is in the right orbit around the right kind of star. It has a large moon to stabilize its axis. It has plate tectonics to regulate its long-term carbon cycle. It has the right amount of water. The list of lucky coincidences is long. The anthropic principle notes that, in some sense, we should not be surprised by this, because if the universe were any different, we wouldn't be here to observe it. A more design-oriented version of this frame might see this fine-tuning as evidence of a purpose or an underlying intelligence. From this perspective, a mass extinction might be seen not just as a system failure, but as a moment of profound significance in a larger cosmic story, a painful but perhaps necessary step in a process leading towards a certain outcome, such as the emergence of conscious observers. The awe here comes from the sense of being part of a grand, mysterious, and perhaps purposeful narrative. What's crucial is that both of these frames can be held with profound humility. The emergence frame requires the humility to accept that we are the product of a blind, contingent, and undirected process. The design frame requires the humility to accept that if there is a purpose, it is likely far beyond our comprehension. Both perspectives, when held with an open mind, lead to a similar place, a deep sense of wonder at the existence of our world and our own conscious experience of it. Whether we see the Earth as a magnificent accident or a mysterious creation, the result is a powerful feeling of gratitude for the privilege of being here. The Permian story can be read through either lens. It can be a case study in the nonlinear dynamics of a complex emergent system, or it can be a chapter in a cosmic drama of destruction and renewal. The choice of frame depends less on the data itself and more on the kind of questions we are asking of it. After this vast journey through time and scale, let's bring it all back to the most personal level. Where are you in this story? The answer is not that you are a distant observer, looking back at the past. The answer is that you are inside the system. You are a living, breathing component of the current iteration of the Earth's biosphere, the one that was born from the ashes of the Permian and shaped by the subsequent 252 million years of evolution. The story of the Permian is not something that happened to the Earth. It is something that happened within the Earth system, and you are currently within that same system. This is a profound shift in identity. We are not separate from nature, studying it from the outside. We are a part of nature that has evolved the capacity for self-awareness. The atoms in your body have been cycling through this planet's systems for billions of years. The oxygen you breathe is a product of the biosphere. The water that sustains you is part of the global hydrologic cycle. The fundamental operating system of your own biology, your DNA, is a direct descendant of the code that made it through the Great Dying. You carry the legacy of the survivors within every cell of your body. This recognition of belonging comes with a kind of quiet, embodied agency. If you are part of the system, then your actions, however small, are part of the system's functioning. The way you interact with the energy, water, and material cycles around you is your contribution to the planet's overall metabolism. This is not a burden of responsibility, but a simple fact of existence. It is an invitation to see our daily lives not as separate from the great planetary story, but as our unique and personal expression of it. When you feel the warmth of the sun on your skin, you are experiencing the energy input that drives the entire planetary system. When you watch clouds form in the sky, you are witnessing the conversation between the oceans and the atmosphere. When you walk in a forest, you are standing inside one of the great regulatory engines of the biosphere. Thinking this way dissolves the illusion of separation. There is no environment out there that is separate from us. There is only one interconnected system, and we are an integral part of its present and its future. The Permian story, in its terrifying grandeur, serves to remind us of what a privilege it is to be a conscious part of a biosphere in a state of relative health and stability. It locates us, not as masters of the planet, or as aliens upon it, but as what we truly are, the children of its long, turbulent, and resilient history. So, where have we been on this journey together tonight? We began in the quiet of this present moment with a single, gentle question. What was it like to be on Earth during the Permian extinction? We set out not to find a single final answer, but to explore the question itself, building a model of that lost world from the faint clues left behind in the rock. We travelled to the fossil beds of the Karoo to witness the eerie silence that fell upon the land. We dived into the chemistry of ancient oceans to read the story of a planetary fever and suffocation, written in the language of carbon isotopes. We stood in the heart of the supercontinent Pangea and felt the harshness of its climate. We identified our prime suspect, the colossal volcanic eruptions of the Siberian Traps. But we saw that the story was not a simple one of a single killer. We turned our perspective and saw the event as a catastrophic failure of a complex interconnected system. We saw how the planet's own feedback loops, the very mechanisms that normally keep it stable, turned against it, creating a runaway death spiral. We saw how the death of the forests on land fed the death in the sea, and how the entire web of life unravelled. We have built a story of a system pushed past its breaking point, a story of thresholds crossed and a world transformed into a hostile alien planet. And now, at the end of our exploration, we can re-ask our core question. What was it like? It was likely hot, suffocating, and acidic. It was a world of toxic oceans and dying forests, of violent storms and unrelenting heat. It was the sound of a world falling silent. It was a sensory nightmare. But it was also, for a very few, a world of survival against impossible odds. It was the moment that set the stage for the entire future of life on this planet. It was the end of one book of life and the painful, difficult beginning of the next. As we bring our exploration to a close, I just want to extend a quiet thank you. Thank you for your time and your attention. Thank you for bringing your curiosity to this deep and difficult subject. In a world that often demands speed and certainty, the simple act of sitting with a question, of patiently following the evidence where it leads, and of being comfortable with uncertainty is a rare and valuable thing. These kinds of slow, reflective journeys are made possible by the community of listeners who find value in them. If you feel moved to do so, you can support this work in any number of quiet ways, by sharing it with a friend who you think might appreciate it, by leaving a comment with your own reflections, or simply by carrying the questions we've explored tonight with you. There is no urgency, just an open invitation. The most important thing is that we've shared this time together, expanding our sense of the planet and its long, incredible story. Thank you for being here. The story of the Permian extinction is not one that ends with a neat conclusion. It is a story that should leave us in a state of quiet contemplation. It resists easy summary. It is too large, too profound. So let's not try to force one. Instead, let's allow the echoes of that lost world to settle. Let's sit with the dual truths of fragility and resilience. The world is a system of immense power and complexity, capable of creating breathtaking beauty and diversity. And yet, that same system, under the wrong kind of stress, can unravel with terrifying speed. Both are true. Life is a tenacious, creative force that has persisted through almost unimaginable catastrophes. And yet, the lives of individual organisms and entire species, and even entire ecosystems, are profoundly fragile. Both are true. Holding these opposing ideas at the same time is the work of wisdom. The story does not offer us simple lessons or easy answers. It offers us perspective. It offers us a deeper, more textured understanding of the planet we call home. It recalibrates our sense of time, our sense of scale, and our sense of our own place within this long, ongoing narrative. The ultimate value of looking this far back is not in the specific knowledge we gain about the past, but in how that knowledge transforms our perception of the present. The world outside your window is not a static backdrop. It is a dynamic, evolving system with a deep and turbulent history. The air you are breathing is a legacy of that history. The ground beneath you is the archive of it. The life you are living is a continuation of it. So let's end not with a conclusion, but with a lingering question. Let the curiosity that brought us here tonight stay alive. Let the story of the Permian world be not a closed chapter, but an open door, a door to a deeper and more intimate relationship with the strange and wonderful planet that is, for this brief and precious moment, our home. Let's return one last time to where we began, to this room, to the air you are breathing. Take one more conscious breath. Feel the coolness of the air as it enters your nostrils, the warmth as you exhale. That breath is a physical transaction with the biosphere. The oxygen fueling your cells was created by a living thing. The carbon dioxide you release will be taken up by another. You are a note in a planetary song that has been playing for billions of years. Notice the materials around you once more. The wood, the plastic, the metal, the glass. Each has a history, a story of transformation, a journey from a raw geological or biological state into its current form. They are pieces of the planet, rearranged. The story of the Permian was the story of these same materials, these same atoms of carbon and oxygen and iron, being subjected to an immense and violent rearrangement. It was a story of a change in state. The world we live in today is the result of the new, more stable state that was found after that chaos. The quiet hum of electricity in the walls, the distant sound of traffic, these are the sounds of our own world's metabolism, our own complex system at work. The journey we have taken tonight, from this quiet room to a world of fire and poison 252 million years ago, and back again, is a demonstration of the power of human consciousness. We are the part of the universe that can look back on itself, that can read the memory in the stones, and that can try to understand its own origins. The echo of the great dying is not a sound of despair. It is a quiet, resonant reminder of the immense creative and destructive power of the planet we inhabit, and of the precious, fragile and resilient nature of the life that it holds. The same planet, turning then as it is turning now, in the silent dark.